Jo, oba dva tím si udělám. Jasně. Jo. Hello, hello.
Hello, everyone. Radek, come here.
Wow, I'm so nervous.
Same.
We haven't done this for a couple of years. I haven't seen so many people for a while.
Yeah, but it's great. You arrived and we were able to meet in person, but also welcome to everyone who's joining us online.
All right, so yeah, welcome everyone at DevConf. Let's do first some introductions. So folks, my name is Radek Vokal. I've been at every DevConf so far, and this is Dorka.
Hi, my name is Dorka Valkova. I am responsible for the organization now. I have not been at every DevConf. I think I've been at the past 5 DevConfs. I started as a volunteer, and now I'm standing here. So every volunteer, this is your chance. You'll be here once upon a time.
So first thing first, who's here for the first time? Raise your hand. That's quite a few people. I'm amazed. That means that I will have to explain you now what DevConf is about, right? So here's the thing. How much did you pay for the ticket? 0, right? Perfect. Okay, so that means that whoever paid 0 for the ticket is automatically a volunteer at the conference. You're helping with the conference here. You're making sure that this is a great event, right? So make sure that everyone has fun here. But we also need to leave this room and this venue clean and in the same shape as we get it, right? So please help us out. Make sure that this place stays as it is. And that's the main thing of DevConf anyway, right? So this whole event is organized by volunteers, but it's organized by a large group of people. I stopped counting at some point how many people participated in organizing this thing. And also all the speakers. It's a mix of first-time speakers. It's a mix of some people who've been presenting for a while. A lot of them hasn't been presenting to such a large audience for a while as well. So please be patient with them, give them feedback as well, help them out during their talks, ask questions, interact, participate. This is the main thing that we want to have here, some discussion, and you should really enjoy the conference. But there are some housekeeping things that we need to go through, right?
We can do that now. Yes, we can. So first and most important thing is the schedule. Please have a look at it. It's the main thing. We made some last-minute adjustments, so if you were looking at it yesterday, have a look again. Thank you. I need my notes to remember everything that I want to say. Important thing is that in this part, or in these several sections, there are talks and workshops. On the other side of this street, main street outside, there are meetups and activities. For example, we have physiotherapy every day, so if you want to learn something new or exercise, that's your chance. Another thing, we're transitioning to Matrix, so people who are online might be already there, but you in this room or joining us in person can join the DevConf.CZ 2023 space as well, participate in Q&A, and watch the streams in other rooms. I guess it's up to you. Thing that everyone is asking about all morning is social event. Yes, we're hosting social event tomorrow.
You have to wait for it a bit still.
Yeah. We want you to attend the talks and then talk about the talks during the social event. So it's held tomorrow. It's going to be outdoors. Speakers already got tickets, but we have many more for everyone in here, almost everyone. And we are handing them out tomorrow at 12 near the registration area.
And the venue is still secret, right?
Venue is... Yes, why not?
It's not that far from here, and you'll be surprised.
Yes, it's on the way from here to the city center. It's outdoors, and we'll update the schedule so you'll know where it is tomorrow, probably after 12 or around 12 noon. Another thing, we have an IT museum at this faculty. They were very nice to us and let us use it or show it to you. It will be open in very uncertain times. So we'll let you know either on Matrix or, word of mouth. In here, you might see open doors and arrows pointing there. We have an EMT present or first aid station. It's there near the coffee that's stationed outside. If you need any help, want to report something or want to, suggest something for us to improve, you can stop by at the registration, or you can talk to our volunteers who wear a light blue t-shirt, or to me, even though I don't wear the light blue t-shirt. And last thing, please respect our code of conduct and enjoy the conference.
I'm going to mention one more thing. You don't have to give this to me. As you probably remember, some of you who've been here for some time, the last session of the conference is interesting and you should come because you'll be able to win some prizes. But it's not going to be for free, right? So you'll have to do something. But it's going to be fun. So show up on the last session as well, and join us for some interesting prizes. Before we jump to the keynote, we need to thank the faculty here. We've been organizing this event at Brno University of Technology for about 10
my
years.
Guess. It's
right?
my guess.
So this is just a so beautiful venue. I'm still mentioning to people that when I studied here, it was monastery back in the days, and it looked like one when I was here, unfortunately, and it's so nice right now. So I want to give word to our friend here, Vítězslav, from the university.
Hello. Thank you. Every time I'm wondering, what is this applause at the beginning for? I didn't show anything, I didn't say anything, just I'm here. As you mentioned, we are in the monastery from the 13th century. I hope you will have time to go around and see the beautiful parts of this monastery. The monastery during the era was closed, it was given to army. You know, it's usual to change the soul for the rifle, unfortunately. I think from the 13th century, this was the place where people that were thinking beyond the present horizon, they meet together, they think, they share their, the share possibilities in that time was a little bit slower than today. To go from Paris to Brno take 20 days. I think they talk about their present problems, they shared their ideas, and they were thinking about the future. And I think today you do the same. We moved with technologies, but let's try to think how much we moved on the other parts of our important lives. So I would like to thank you, Red Hat, for doing this conference here.
Thank you.
Thank you very much.
I think we should officially start, right?
Yes, officially.
Okay, let's do it. Let's start right away. So we're starting with our keynote speakers. Come on up, guys. All right, so we're right on time, almost. Let's start with our first keynote. I'm just going to quickly introduce the folks here. The keynote is Become an Open Source Service. Let's give people a few minutes to enter.
No, yeah, absolutely.
Yeah.
This is amazing. We're having DevConf again. Woo! Door closed.
Door closed. I think that's a sign, right? Okay, we'll be talking about open services, and this is an interesting group of people because we have folks who've been with the communities in different projects for a while, who've been in different positions as well, right? Dealing with customers, dealing with developers, doing some real work in developing the services. So it's something that we're all passionate about. We'll be talking about this topic for a while, also during the conference, so not only at the keynote. I think we should do a really quick round of introduction for people who don't know us. My name is Frade Vokal, and I'm currently working at Red Hat as the product manager for a set of services that we call Insights. I've been at Red Hat for almost 20 years now. It's a little crazy. And yeah, Steph, I know you for ages as well.
Yeah, I've been involved in open source for over 20 years. This is not my real hair, in case anyone's wondering, but if I don't wear it, I get booed off stage. I lead a lot of the RHEL engineering, Linux engineering, satellite teams. So many people that I have joy and pleasure of working with are here as well. Over to you.
Thank you. Hi, I'm Simon, and this is my real hair. Yeah, I've been working in open source for something like 15 years, and I've been at Red Hat for 2 years, and I've had the amazing opportunity in these 2 years to work with the very talented people in the image builder team. And yeah, we are the first service of this HMS sort of insights groups, RHEL services to be available publicly, and we're very proud of that and working to make the service even more open going forward.
Thanks. Hello, I'm Roberto Caratalá. I'm a Cloud Services Black Belt, even though I don't know a clue about Kung Fu or anything else. And I'm working for Red Hat more than 7 years, almost 8, and a pleasure to be here beside.
Hello, I'm Tomáš Tomeček. Radek and Ondra Vašík hired me actually 11 years ago.
At DevConf, right?
Oh, yeah, at DevConf. And I never thought that I would be doing a keynote here, and I like doing short introductions.
Thank you. All right, so let's give you guys a first introduction, right? So why are we even talking about open source services, right? Why should we care?
Why do we care about this? I mean, come on. We've all been part of a massive, monumental change that has made the world better. We have brought open source into every corner of software development. I mean, there's proprietary systems is now assumed that somewhere in the stack is a component that someone in open source has worked on, someone here. There's open source services, systems, operating systems, everything you can imagine that has open source permeated throughout everything. And this has brought humanity much further than proprietary software could. So when you walk into a Red Hat office and you see one of these signs from Mahatma Gandhi, you can easily assume that, okay, we won, we're done, this is great, we have now utopia, it's all wonderful, let's go home. And we're here to tell you that this is not the case. There's a challenge ahead of us. There is a challenge to open source that if we don't address and we don't adapt to, will become a threat. And I'll explain to you why that is. Think back on your first open source change that you made to a component or something you were running. Now, for many of you, this has been around for maybe the whole time you've been working on software. But for some of us, it blew our minds. Think back to when the first time you could actually change something, change the behavior of something on your computer. And you finally put in, maybe you changed the color of something. Maybe you put in a printf. Maybe you logged something and you changed the output of a command. And it just blew my mind that this was possible.
I'm surprised you found my first patch.
This is your first patch. It's very good. I couldn't find my first patch. I mean, I didn't keep it. It was garbage. It was changing, I forget, something to Pig Latin, and it was in fetch mail, I think. Think about what makes this actually possible. What makes this possible is that you have a copy of the software running on your computer. This is what made this possible for me. And the source code was shared in a way that I could actually change it, I could rebuild it, and so on. And the problem that we face is a lot of people, a lot of us, but a lot of people in the world no longer actually want to run a copy of the software. They want you to run that crap that you wrote. They don't want to run it. And they want to experience the output in the form of a service, in the form of an API that they call, in the form of infrastructure as a service. In one way or another, they want to use the software without actually having to run it, much less make a copy of it themselves. And so we run into a paradox here, a conundrum that we need, and I'll walk through this with you. The first thing is that open source thrives when it can convert some small percentage of the people who are using that software into contributors. Now, some projects, this happens a lot. This happens at a fantastic pace where half the people become contributors, maybe developer tools or things like that. In other cases, it's a small fraction, but there's some function here of people who are using the project actually decide to make a change or help in some way. And conversely, it starves when that can't happen. So if you prevent that function of users becoming a contributor to the software, open source starts to atrophy, regress. But our open source practices, most of them require that you operate a copy of the software in order to change it, in order to even get the idea that you could make a change, in order to play with it, in order to introspect it, in order to understand what's going on. But at the same time, the users of a service literally chose not to run the software themselves. They're using the service mostly because they want someone else to run it, or in some cases, it doesn't make sense to run this thing in another place. It makes sense to run it in one place. So they're unable, unwilling, or just doesn't make sense to copy the software and operate the software. So we're at a paradox, a place where when we put all these things together, it doesn't add up. It is very hard to contribute to open source services. It's not natural. And the mechanism that we use that underpins much of open source, licenses, copyright, is about copying software. And therefore, and in services, you don't need to copy a service in order to have that software be successful, that software be used. So although all those ingredients, we can still use them. We're not going to throw away open source licenses, for example, but they are not sufficient to solve this paradox. And so imagine a world, we're not there yet, but yes, imagine a world where you can actually go and look at what's running in the service that you're using. You can see the code, you can see the software. Imagine when you call the API, you can understand what the hell is going on under the hood. You can see the same way you can with a stack of Python or Node.js on your own machine. Imagine you could make a change and experience that change without operating it yourself. You can make that printf or that change, or you could translate it into Pig Latin, or you could change the color of something in a service, and you can actually see the behavioral difference. That is a world where open source actually works with services, with software as a service. So,
I think we need some rules, some guidelines, right? We actually...
Yeah. Well, exactly. And this is real today. So that's what we're here to talk about. It's not about, we wanted to introduce the challenge, the paradox, but what we are doing to start to address this problem. And so many people are involved, so there's so many different ingredients to this. One of them is that together we figured out what are the basic requirements for an open source service. It's not just an open source license. It's not just sharing the code, although that's important. The first requirement is that you do share the code. It's the same with a project, that all components and all the assets in the service are shared under an open source license and available to the public. That's fundamental, of course, but it's insufficient. And the second fundamental part that we need is that others can contribute in the same way as a team working on the service can. Whatever that mechanism is that you use to work on the service, to deploy, to review pull requests, to accept those changes, to run tests and so on, others need to be able to do it in that same way. And by meeting these basic requirements for an open source service, people can then take it further. They may not take it further, but they can take it further to perhaps operate it somewhere else, or add capabilities and ways of working that people...
This is all great, but is someone already doing all this stuff?
Yes.
Really?
We're going to blow your mind, Rada. this is happening today. I mean, it's not all perfect, but that's why we need to work on it together. So.
I think Tomasz is actually working on something. He raised his hand immediately when we start saying someone is actually doing this for real, right? This is the slide, sorry.
Yeah, we definitely need to make it and get it further. Okay, so I think you might be confused while looking at the slide, so don't worry, that was my intention. But my colleague said that maybe I should explain what's in there. So I tried to collect a few techniques we are using in our open source services and explain. So on the bottom you can see, that's my favorite, it's database dumps from production. And they are super helpful for everyone on the team, and especially for the outside contributors. When you are working on your change locally, you can load it up with the production data and see how the change would feel in the production. That's really amazing. Just one pro tip, don't forget to remove all the passwords from the dump. and the whole top is filled with documentation, and I can't stress it out how many times this saved my butt when I was trying to work on our service and I didn't know which OpenShift command I should run or how to access this or that, and then I open our documentation, which is like really perfect for deployment and for the architecture, and I immediately knew what I need to do to like keep the production service running and don't trash the secrets or something like that. So it's really essential, especially when you are struggling or there is some problem and you need to solve it like as soon as possible. Like make sure that your deployment documentation is flawless. Yeah, on the top right, sorry that shouldn't be there, Simon will talk about it. But what Steph said, so the minimal requirements are all the assets are open and everyone in the public can contribute. And it's really just minimum. I mean, when you meet that, when you open source your code and collaborators start piling in, like that's the beginning for you. And there are many things you can do. For example, in our service, one thing that really helped us was opening up our planning process, because we would always get these questions like, so what are I working on next, or what's the current epic, or even within the team we sometimes didn't know what we want to work on. And as soon as we made Kanban board on our GitHub namespace, and everything's open, all our epics, what we are working on right now, it makes so many things much easier. So before I hand out the microphone, I would like to challenge everyone and think about what should be on this slide, because I collected a few screenshots here, and now that I kind of see it on the little screen, I know there are many things missing, and I would really love to see more solutions and make it easier for everyone to, as Steph said, so I can experience a change I'm working on and I don't need to deploy anything. Someone will do it for me, some system. So think about that, and maybe when we do this in 1 or 2 years, this screenshot, this slide will be so full that you won't be able to see anything.
Right, and Tomasz, this sounds way too easy, right? I think there must be something missing. It's not just about the code of the service, right? You have to still run it, deploy it somewhere. What are the things that we're missing? Roberto, help me out.
Yeah, please.
When we are talking about software as a service, it's not only about the code itself. The service and the service itself is much more than just the code. It represents, for example, the service represents the tip of the iceberg. For example, we have much more value in the service rather than this. If you show, we have the best practices that represents and manage the different services at scale. We have the automation and the infrastructure that are running as well. We have the operational processes, the interconnected services, and all of these components and pieces are backed up by open source projects and repositories that you can enable the users to influence and to make contributions in order to make changes to the software and the services that they are using. For example, Azure Red Hat OpenShift is a jointly designed service that runs in Azure itself, and is designed by Microsoft and Red Hat, and it's open source. So you can go there, you can contribute, you can open issues and influence to the different software that you are using at scale.
So Roberto, I have a challenge, right? So I know that there's a bunch of services out there. I'm running some of them. I'm using some of them. How can I tell that this is an open source service and I can just start contributing to that, right? Simon, you have an answer, right?
Yeah, I mean,
Go for
it. That is a very, very good question, a very valid one, because it sort of ties into all the other things that were said before me, like the thing that Steph said. You know, we're sort of used to a certain way of working with open source software. We know, we download a software package, we have an idea of, where's the source? I mean, we've just downloaded it. There is a disconnect, though, with services where we don't necessarily know where the source is. Or we don't know where the documentation is, or we don't know how to find the standard operating procedures or the best practices of the specific team that designed this very service.
But you don't even know that the service is open source.
Yeah, exactly. Right. You might not even know that a service is open source. That's even more fundamental. And the only way you can do this is by embedding something in the service that guides the user to how to introspect the code, or that shows it at the first glance, oh, this service is open source. The same way that a fork me icon on GitHub tells you, oh, I can fork this code, I can actually work with it, it's open. And this is, I think, something that we really need to work on, that we're sort of piloting on some of the services that are open already, as you can see in this screenshot. And the idea is to really sort of connect the two dots, the running service down to the source code, and to give users a way to, first of all, inspect the code and understand why an API is maybe not behaving the way that you're expecting, or that the documentation told you it would behave, or even how you could change it, and how you could maybe introduce some typing or something into the API and make sure it doesn't break. But I mean, one thing that we haven't really addressed is, why should any business care about this? Like, why should anybody invest money into this?
So here's the thing, right? So at the end of the day, the services that we're all working on and that we want to open source, someone wants to monetize them, someone wants to benefit from them. And I have an observation as a product manager about services that, from my perspective, are becoming successful. And there's a component that we didn't mention here, and I want to highlight here. A lot of these like services and things that you see, projects here, open source projects here, are actually opening up their ecosystem for further contribution. Something I would call a midstream, right? Where you can build extensions, integrations, plugins, different connectors. And this allows different people to pick up these services, pick up these projects, and extend them for their specific use cases and different purposes. Extend them beyond what the initial authors of the service even thought about, right? If you look, again, at some of these examples, you basically realize that these are projects that were very much focused on a single use case at the beginning, single purpose again. But because they thought about, again, plug-in-able infrastructure, extensions, and additional things, these became hugely popular. And again, this midstream idea where different people can contribute on top of the service. They have access to APIs, they have access to a sort of a playground, mock data, and these kind of things is a huge thing. And again, that's where I see the services being successful, but also then solving problems and solving challenges for some of my customers that, again, the initial authors of these services haven't even thought about. So I think that's something that we should all think about as well, how to not just open source the service itself, how to open source the ecosystem around that so others can easily contribute on top of your service, within your service as well. We've talked about a lot of things here, and we've touched on these things, right? But we need to go deeper. And because of that, we actually have a couple sessions during DevConf, and we welcome you to join these and challenge us and tell us how wrong we are, or whether you're already doing something else and it works for your community, your use cases. Let's do a really quick introduction about all these talks that we're going to be doing. So, Thomas, you and Neil are doing the first one, right?
Oh yeah, so we spoke about open source services right now for a few minutes, and you can actually experience the contribution process tomorrow, 10:15. I don't know which room, but the title of the talk is up there. So we have prepared a workshop for you when you can try contributing to our open source service. It will be just the front end, not the back end. And yeah, we invite you there. For any successful contribution, we have prepared some nice presents for you. And for the people who will come there, we really would like to challenge and think about how can we even extend that process to the back end, for example, so that it's so that anyone can make the contribution and experience it very easily and not build thousands of Docker images or whatever and try to set it up themselves. So please come by.
Perfect, perfect.
So
I see Neil over there. Hey. Roberto, you're doing a talk with Marcel here. Torsten as well, right? You're joining to session too? No? Just Marcel? What is your talk about?
Yeah, if you are wondering how you can start contributing in these open source services, in focusing, for example, the cloud services, well, Marcel, Held and I, we will be talking about how much open source is in the cloud services, and we will analyzing and discovering the different open source projects that are using in real production, managing the different managed clusters that Red Hat Cloud Services manage across the world. And we will also present these different repositories, projects that you can get, you can influence on them and get inspiration on it in your own projects. So you can get some ideas in order to make it better. Perfect,
perfect. Simon, you're talking into more details about this small icon, right?
Yeah.
Is it just about it, or is there more?
Yeah, that's it. So my talk will be very short. It will last like 2 minutes, maybe max. So my talk is on Sunday afternoon. So the first challenge, of course, is for you all to be there because it's Sunday afternoon.
But let's challenge everyone. So people don't know that your service is open source. Many of you run open source services. No question, you meet those requirements. People can contribute, and your code is shared. But everyone who's walking through, the users, don't know that it is open source. They don't know what code you're running, and they don't know how to contribute. So come to Simon's talk.
Thank you. Yeah, very much so.
What are you doing?
Okay, I will make it longer than 2 minutes, but also not too long. Yeah, but the idea is, of course, figure this out. We have a proposal. We're piloting something already. You could see it in the screenshot. It's real. It wasn't a mock-up. And I'm very interested to hear your thoughts, of course.
Yeah, thanks for the spoilers, Steph. The important thing is that during the conference, you'll find some other talks. I was going through the schedule. I found these interesting talks from Elad, Nicholas. You guys should join these. David, I see you over there. You're talking about some of the services as well. I've seen some other people here who are passionate about this topic as well. So go grab them as well, join their talks, challenge them as well. So that's the main thing here. So B, we've thought about doing some sort of a competition about you contributing to open source services. I think we should still at some point do this, that would love to see your contributions as a result of DevConf. So after DevConf, if you contribute to any of the open services here, you want to send us your patch, we might actually send you something, some gift, if you do so as a result of this keynote, right? So we know we're successful. Right. That's the way, right?
Exactly. And let's not pretend that this is easy. Solving this paradox is hard, but we do hard things, and we do them amazing well and at scale. We have changed. Open source wasn't an easy thing either. We all worked hard to make that true. This challenge is an exciting one, but it's difficult. And when you believe, oh, this is a problem that's going to prevent this from progressing, for example, with accessing data, that one comes up a lot. That just tells us that we need to work together to solve that problem. Join that workshop. Start to figure out with Tomasz and with Neil how to solve that aspect. Bring an idea, work together on this, and we will be able to solve it together. We'll solve this paradox.
Perfect, perfect. I'm going to say these are the famous last words, right? So again, join us in these sessions. If you have any questions right now, we still have a couple minutes, so bring them up. Okay, there you go first. Just yell it and we'll repeat it.
How do you think about solving the development environment problem? This is the problem I always have in services. You want to write a change, you want to test it, and it takes 2 days instead of a day. So how do you solve that?
It's a quickly repeat that, please.
So the question is, how do you solve the development environment problem? Where you can quickly bring up your change and not have to wait days for an environment that you can run it in.
I would say we already have the solution. It's containers. I mean, we have the recipes how to build them, so create them, and then use tooling to get them all together, and hopefully even with that production data inside, and you can have the development environment locally. Like for me, this is already solved. I know that can be still be improved over time in future, but for me, it's done. So I'm really curious what everyone here thinks about it, so feel free to approach me about it.
Like the question. He has been contributing to too many projects not to have an answer to that question.
All right.
What's your take on it?
I saw pity. Yeah.
It's for some projects that works. Projects where I specifically have this problem right now with Bodhi, the Fedora update service. To get a development environment working, you need 5 other services, and there are container definitions for those. You need to run the virtual machine. My laptop gets a little sad when you come to run forward.
Right. So the truth is that, as you mentioned, some of the services are too huge to be run on your laptop. You need a playground. You need a testing environment.
So join this workshop, because that's literally the thing that needs to be solved, and that, like Tomasz said, already has a working solution for the front end, but we really need a deeper solution. Like that is literally the nut to crack. Totally agree, and I'm glad we're working on it together here.
All right, I see one more question in the back first. I'll get to you, Lukashi. Someone was raising hand.
Pity had his hand up.
Yeah. So it works for some projects. That's good to hear. Okay. Lukashi.
So let me just say thank you. Thank you, because this has been the fundamental issue that you actually pointed out at the beginning of the presentation, is that something that bothered me for the last couple of years, right? This fundamental change in how open source works, because everyone is using it, but they're building the services and you can't integrate into them easily, right? So we have to have this mind shift, right? From the open source perspective to actually go and build out this ecosystem, as you've been talking about, right? So that we can contribute to those services. And the providers of those services are aware that this is something that's beneficial for them. So I just wanted to say thank you.
Perfect. Perfect. Thanks, Lukashi. Anything else? Any last question? Oh, there's more. Okay. Hold on. I'll hand over the microphone to you.
Thank you. I noticed that licensing didn't come up as much during the talk. Do you think there's a perception that that licenses for open source services are maybe not so effective? If there is a perception like that, should it be changed? How could it be changed? How do you think open source and free software licensing fits into the picture that you're painting here?
This is a good topic. So the challenge that we have is not that open source licenses don't work. They work fine. FOSS licenses work. GPL works for services. There's many licenses that even are even more aggressive, like the AGPL on services. But they are insufficient. Because you don't copy, or you don't need to copy the code that's running in software, they are not the enforcing mechanism. They're not the thing that actually underpins open source services anymore. And that is the problem. So they're good, but they're not sufficient for what we need to pull off here.
I think that part of the challenge is also that you need to be able, for someone who contributes, I'd say, live to a system, let's say the contributor is a banker or something like that, and they want to really make sure that what they have contributed is actually what is running on the other side. So I think that if you want to do that correctly, you also need to have a really good chain of trust all the way. And I'm not trying to advertise for the talk that I'm going in 1 hour, but just in case. So chains of trust are important. I think we are starting to know how to build that at the VM level, at the workload level, etc. I'd like to advocate for building that in the programming language themselves, and that's hard. Don't get me started on that, but that's really something that we need to probably put some emphasis on. So really integrating that at the low-level API level when you have an RPC mechanism, that this RPC mechanism can not just send data over, but send a proof that the other side of the API was this version, that it executed in this environment, and it gives you a cryptographic proof that this went well. Otherwise, it fails spectacularly, and you know it failed.
Okay, thank you. So this was very good advertisement for your talk. So thank you for solving one of the challenges.
Yeah, and data security, data residency, these type of things, those are all challenges for services. And yes, we do have some additional talks about this type of problem here as well. Folks, anything else? Any other question? If not, we'll let you go right now. Grab some coffee. It's going to be exhausting 3 days, I can promise that. And thanks a lot. You've been a great audience.
11, окей. No to je full screen, ale já to prostě chci ten jeden slide. Máme toto na streamu? Almost killed me. I guess we can get started. So, hello everyone. My name is Vitaly. I am from virtualization engineering team at Red Hat. And normally I work on various public clouds and third-party hypervisors, making sure Linux is the first-class citizen there. I'm also a sub-maintainer in KVM, working on things like Hyper-V enlightenments and various x86 things. Today I'm going to talk about supporting the new thing in the cloud, confidential VMs, and what we can or should or must do in Linux to make this all work. So if you've been following this cloud landscape over the last couple of years while sitting at home, then you could have noticed that all major hyperscalers released something which is called like confidential VM. I think Google was the first one with AMD SCV option in 2020. AMD SCV gives you memory encryption, and basically that's it. Then we have an offering from Microsoft Azure. Since last June, it's even in GA, and they do AMD SEV SNP, which is like an advanced version of AMD SEV, which not only gives you memory encryption, but it also gives you like register encryption or register protection and integrity protection. We now have Intel TDX, which is a technology very similar to AMD SEV SNP from a customer's perspective. The implementation is very different, but for customer characteristics, it's similar. And Amazon has just released SEV SNP option for their existing C6, M6A, R6A instance types. So you must have been wondering like what these confidential VMs are about and what do they give you as a user, right? Why are they better? Why would you want to use them? And basically, what they promise is that these VMs will keep your data confidential. It's like a bold claim, but then what does it really mean? Well, that data confidentiality means that nobody but the owner of the data can get access to the data, right? And in case of VMs, there is always the host which runs your VM, right? So the confidential VM technology is something which allows you to remove the host from this trusted base. You don't need to trust your host anymore, right? So even a malicious or compromised host cannot get access to your data. However, all these confidential VM technologies give you no additional protections from within the VM. So if you have some application running in your VM, and this application was compromised, hacked into, it will still allow for data leakages, right? The confidential VM technology protects your VM from the outside, from the running host, but it doesn't protect processes inside this VM. Another thing that you must also remember that none of the confidential VM technologies give you any guarantees that your VM will actually gonna run. Because if the host which runs your VM is compromised, somebody can easily disrupt execution of your VM, basically terminate it, or just don't allocate any time slots for it to run. This is always possible, right? So it only protects your data. It doesn't allow data to leak to the host, but nothing else. So when we're talking about like data protection, normally we talk about protecting data in runtime, at rest, and in transit. I'll start with the transit because it's not really confidential VM specific. We've been protecting data in transit for years because we never trusted our networks in the first place, right? We are working over like public Wi-Fi or who knows who administers all these like routers on the way of your data. So there are like cryptography-based solutions how to protect your data while the data is in transit. What confidential compute technologies give you on a CPU level is something which helps to protect the data in runtime, right? Because when you have your app with your confidential data being executed somewhere in the cloud, right? Where is your data? Your data is likely in memory because you need to process the data. You have some of this data in CPU registers because you cannot really operate on memory all the time, right? To make an operation on your data, you need to put it in the CPU. And these confidential compute technologies, which are basically newer CPU features, they allow to hide all this from the hypervisor. As I've already said, AMD was pioneering this with their SEV. And yes, I have to make a caveat that I'm only talking about the technology which allow to basically protect the whole VM. There were technologies in the past which were designed to create confidential enclaves. And these are technologies like Intel SGX. But they don't protect the full VM. They protect certain applications which are specifically built to work with these enclaves. So there was AMD SAV. And AMD SAV protects your memory. So your memory is always encrypted. And only the guest can decrypt it. However, it gave you no protections for CPU registers. So whenever your data is in CPU registers, it can be seen by the hypervisor, which significantly limits the protection. Because basically, hypervisor can stop your VM every cycle and take a look at what in the registers, right? So it's really not hard to steal your data, even when the whole memory is protected, even by observing CPU registers, because once in a while, you will have all your data in CPU registers. Then AMD came with an upgrade, which was called AMD SEV ES, which is encrypted state, where they also hid all the registers. Now, the hypervisor cannot observe the registers. What was missing there is integrity protection. So the hypervisor can do things like, imagine you have two encrypted pages. And the hypervisor can just swap them for your VM. So it cannot see the data, but the behavior of your VM is likely going to change. And you may, for example, do I/O from the memory you didn't want to do the I/O, right? So their latest, SEV S&P, it gives you these integrity protections. So the hypervisor will not able to do any of this. And the last but not least is protecting data at rest. Because once you've done processing some piece of data, you will likely be putting it to storage. And the storage comes from the host. You must be sure that it's also protected. So how are you going to do that? Yes, I've already said about these technologies. There is support for almost all of them for the guest side in Linux kernel nowadays. There is still something missing on Microsoft Hyper-V side to support these technologies with their hypervisor. It's coming. The thing is that Microsoft, they always do things differently from the rest of the world, but yes, we are getting there. Now, I'd like to talk a little bit about protecting data at rest. First, let's think, what do we really want to protect? It's kind of obvious that you want to protect your sensitive data, the data your application is processing. This must be confidential. This is great, but then you have your operating system. And if we are talking about generic Linux operating system, it has a number of things which you would like to protect from the host. Some of this data, think about binaries, they are built from open source. They're not any secret. Everybody can get the same binary of bash as you have, right? You don't want to hide it from the host, but you want to at least write protect this data. But some of the data, even operating system data, must actually be even read protected from the host. Think about your SSH host key, right? If the host is able to steal this, it can try to impersonate you and present some other VM, which will look exactly like your VM, right? For general purpose operating systems, normally to resolve the problem, we want to do like full disk encryption, because encryption also gives us integrity protections, right? Even though we have plenty of stuff which we don't want to hide, it's easier to think about it. Let's just encrypt everything and beat it, right? We've done this with Linux for years. We have things like LUX, which is great and which works and which is able to create an encrypted volume for you. Like, you can be using this on your laptop, in installer, you provide a password, and then everything is encrypted, right? So what needs to be done there? The problem with confidential VMs in the cloud is that you need to think how the guest is going to get the password, right? Or the key, or anything, because these must also be protected from the host. So you may want to do something like, OK, when my VM boots, I'm going to go to the console and enter some password and decrypt my root volume, right? But first, it's really inconvenient, right? You don't really want to have to go to the console every time you are starting a VM on the cloud. But that's not the main problem. The main problem is that this is like inherently insecure, because this virtual console is emulated by the host. So the host can easily see what's going on there, right? So once you've entered this password on the console, you're done, right? The host can easily get to your volume after that. So we must come up with a way for the guest to receive the key in an automated fashion, but we need to make sure that we are giving the key to a true confidential VM. So for example, that its memory is fully protected from the host, that the host won't be able to steal it. And we must be sure that everything which was executed in this virtual machine before that is good to certain thing, because if the host managed to, inject something in your boot chain which is untrusted, then you cannot give any sensitive information to such VM, because it will be stolen from you, right? So how are we going to do this, and namely, like in Linux? So let's take a look at how Linux normally boots, right? That's a very high-level generic picture of what's going on. You have some platform firmware, which in modern cases is like UEFI firmware for x86. Then you will have a bootloader, or actually a chain of bootloaders there. After that, you boot your Linux kernel. Linux kernel takes usually like initramfs, and then it has all the drivers to mount your root volume, switch there, and start executing from there. So we want to do full volume encryption. Obviously, we cannot encrypt everything, because then we get into this like chicken and an egg problem, right? If the whole disk is encrypted, who's going to decrypt it? You still need to have some code which is going to decrypt it. And you cannot delegate this to the host. You don't trust the host anymore. Of course, there are solutions with like host-based volume encryption, but you cannot use them in confidential VMs. So which options are on the table? The first obvious option is, let's basically keep our bootloader unencrypted, right? And encrypt the rest of the system. Maybe good from some perspective, right? Because we are reducing this like unencrypted surface and the code which we must verify in some different fashion, right? We cannot rely on the full disk protection for the parts which are not encrypted, right? But then we need to do quite complex tasks in bootloader. And normally, we want bootloader to do as little as possible. So another option would be to make Linux do the encryption, right? So let's keep Linux, and it's initramfs unencrypted. And the main advantage is that we can use standard Linux tools, right? Linux already knows how to encrypt volumes. We don't need to do anything much. But then we get into a situation where all these three artifacts need to be somehow verified. And this includes like Linux initramfs. So summarizing these two like options, right? We can do encryption with bootloader, but yeah, we then need to have a bootloader we trust, and in open source world we unfortunately don't have many options for that, right? We have to teach bootloader new tricks, like work with complex devices like TPMs in a way we want. And the problem is that when we are writing a bootloader, we cannot use any existing library from Linux because, well, it's like a very different environment. We will have to either like borrow the code in the bootloader and support it ourselves, or, yeah, write it from scratch. Usually we end up with writing everything from scratch in the bootloader by saying like, oh, we are going to get away with a very simplistic something, then it grows, and then it has its problems. And like remember that this part needs to be completely trusted by you, right? Because this is what's going to protect your data. Unlocking by Linux and using standard Linux tools seems to be a bit better. At least some like major Linux vendors seem to be converging on this, because for, you know, like we don't need to re-implement anything. We already have the tools. But then, as I showed you, we have bootloader, we have Linux kernel, and we have initramfs, which all remain unencrypted. We need to make sure that they are trusted somehow. So how are we going to do that? Well, how do we usually check the integrity of the boot chain in Linux? We have two main technologies. One is called secure boot without a space. The other is called measure boot with a space. Don't ask me why. Crash course for those who don't know what these things are. Secure boot is basically establishing a trust chain from the hardware, where we check the signature of every binary we load before executing it. We start with Microsoft certificate, which is embedded in hardware. Then we load some bootloader. Then bootloader loads kernel and whatever. And every artifact which loads the next one is supposed to check the signature on it, that it's like a good thing. Then we have measured boot. And measured boot means that everything we load and every significant fact about system boot gets measured in TPM, which is a device, which is a chip in your system, either physical or virtual, and which can basically record a sequence of events. And this is great, but none of these currently cover initramfs or kernel command line, to this matter. So to make things better, right, in systemd community, people came up with a concept called unified kernel image. And unified kernel image is a very simple thing. It is basically, let's take our kernel, initramfs, kernel command line, bundle them all together in one UEFI binary, and sign it. That's the most important part. Once we do that, if we load this and the signature is correct, we can trust this whole thing, right? So, sounds like great. So, how do we build it, right? We take something which is called systemd stub, which is a really, really simplistic loader, which basically will take out from itself the kernel, the initramfs command line, put this all in memory, check the signature. OK, it all matches, and it's going to launch it. Nothing else, right? We can use secure boot and now also check the initramfs, right? Because that's fully trusted. We are going to grant the key to our data to it. In Fedora RHEL systems, if you use them, you can build UKI with a standard Recat tool. Same way you're building your initramfs now, but you can say like -minus UEFI, and it will build a unified kernel for you. And as it's a UEFI like PE binary, you can load it directly from your firmware or from something like shim bootloader. You don't need complex things like grub. Although we are actually working on adding support to grub to load UKIs even for BIOS booted systems, just to be able to reuse the same image with unified kernel everywhere, including on BIOS booted virtual machines, right? Because otherwise we will have to provide two separate images, one for UEFI and for confidential, another one for BIOS booted. We don't like that. Patches are on the mailing list. Eventually, we hope that are going to be merged into grub. So how does this all work, right? Just to give like a high-level picture of how we boot and how we get the key, right? So we start with UEFI and firmware, and then we rely on secure boot. So we check the signature of the first stage bootloader, which in Linux is shim. Shim is signed by Microsoft, if you don't know. It doesn't change very often. It's very simplistic, and its purpose is to basically carry a vendor certificate in it. So we don't have to go to Microsoft with every kernel build we do, and every UKI build we do to this matter, right? So as I told you, yes, you can boot your UKIs from firmware, but if you want to do it with secure boot enabled, you will have to go to Microsoft and ask Microsoft to sign your UKI, which may not be what you want. So we do it through shim, same way we do grub. But then from shim, we check the signature of the UKI, which in our case, for example, in case of like Fedora and RHEL, is going to be signed by Red Hat already. Every binary we load gets measured into PCRs. So these PCR registers, yes, and I'm sorry for not explaining much about what PCRs are, but think about them as like extendable hash functions. So the previous value gets extended with the next one. So the only way to arrive to the last value is to go through the chain of extension with the same hashes. From when UKI boots, right, at this point we think that we are safe. We know all the measurements, so we can create a policy which basically says, OK, if your system is in this state, this is a good state we know. And then we can give the root volume key to this VM. Great concept comes with limitations. Your initramfs is now static, right? Previously, you were building it on the target system. Now, it's built by your vendor, so you cannot put more stuff there anymore. Or, I mean, you can, but then you will probably have to sign your own kernel, right? Which defeats the purpose if you do it. So, for example, now in RHEL Fedora, we ship a package called like kernel UKI vert, and vert is there for a reason. We put all the drivers which we think you might need on popular cloud and virtualized environments like Vert.io, VMBus, NVMe, stuff like that. And we say, well, this should be enough for major use case. If you need more, unfortunately, you have to talk to us. You'll have to open a Bugzilla. Please put more drivers in the UKI. Yes, you can rebuild, like literally, right? You'll have to deal with signatures. Shim offers you this like mock mechanism. So basically, you can enroll your own keys which are going to be used in secure boot. That's one thing. Another now static artifact we have is the kernel command line. Previously, we used to put things like root equals something on the kernel command line, right? Because we were creating on the target system. We cannot do this anymore. We need to have a command line which works for everyone. So honestly, we can't really put much there. And basically, Fedora and RHEL ship with something like console equals TTI S0 TTI 0, and that's it, right? So we need other mechanisms for very standard tasks, like how to find your root volume, right? What's going to be the root volume if we cannot pass this parameter anymore? So we rely on some features from systemd which allow for auto-discovery of the root volume. You may still need to modify your kernel command line in some cases. For example, we realized that we have things like crash kernel equals something on the kernel line. And if you don't know what it is, you just reserve some memory for a crash kernel. In case crash happens, you boot into the special like kdump kernel, which is just going to save your memory to a file. So you can file a bug with your vendor and say, oh, my kernel crashed, here is the logs, here is the memory dump. We cannot come up with one-size-fits-all solution there because different systems may need different sizes. So there is a recent development in systemd project for systemd stub. There is a signed extensions mechanism. Again, so basically you can produce a signed file, put it on your EFI system partition, unencrypted, and then it's going to be sourced, if the signature is correct, of course. They will either come from your vendor, or you will again have to deal with issuing your own secure boot keys. Yes, I've talked a little bit about the TPM policy when we release the secret, right? We release the root volume key, right? What would this policy be? What do you need to check to say that your system is a good state? First, as we heavily rely on secure boot, you must be sure that secure boot was actually enabled on your system, right? So at least this must be included. Then you must be certain that the artifacts which you trust were booted. And then you have options there. You either trust the certificate which signed these artifacts, meaning basically saying like everything built by Red Hat is trusted, right? Or everything built by Canonical is trusted by me. And then your policy will only contain the certificate. Or you can be more strict and say, I want to make sure that these exact binaries with these hashes were used in the boot. So I only trust these binaries which I know. Currently, for example, for Azure confidential VMs, we use the second approach. And the reason for that is that we at Red Hat use the same certificate to sign our kernels and our UKIs, which makes them indistinguishable from the certificate perspective. And this means that somebody can take our normal kernel with any initramfs he wants and boot that. And that would pass the policy if we just check the certificate. From a random initramfs, he will be able to steal the password for your data. We don't want to allow that. So we actually bind the secret to this hash of the particular UKI and the bootloader before it. So, all right, you trust your vendor, you did everything this yourself, and put it on the cloud, and your VM has booted. Can you start using it, right? It must be confidential, right? On this web UI, it tells you green, I've booted. Well, ask yourself a question. How do I know that this is actually the VM, the confidential VM, and not something completely different? Think about this attack that a host creates non-confidential VM somewhere else on non-confidential hardware, but then changes everything inside it. So when you log in and you ask, am I confidential? It will tell you, yes, yes, I am. I am confidential. You need to find a way to attest this system, basically to prove its properties, that it's like a true confidential VM, that it was using the image you expect, that all these technologies which we just mentioned, they were actually used, right? And it's not some completely different image. And this process is called attestation. I encourage you to come to the next talk by Christoph. Christoph is over there, who is going to talk about establishing a chain of trust, like to make sure that what you're using is what you expect you're using. There are some other solutions like for attestation service like cloud-based services. There are some from your cloud vendors like Microsoft Azure. There are some coming from hardware vendors like Intel is working on something called Project Ember, and which is like a cloud-based attestation server. And yes, I also want to talk a little bit about the remaining potential attack vectors, but I think we are already over time a little bit. So I'd rather go to Q&A right away. Hope we still have some questions. Thank you. Yes.
So in this confidential VM, the UEFI boot firmware would still run inside the protected VM. So presumably, in order to do attestation properly, I will need to be able to build that and actually get it to PCR so that I can check that the cloud provider has compromised the UEFI firmware.
Yeah. So to rephrase the question is, what do we do about the firmware, like UEFI firmware, right? It's also in the picture. It's what gets started first in the VM. We need to have some trust in this artifact. So two ways. First, for example, what Microsoft does with Azure today. They have some sort of an attestation mechanism in their infrastructure. And the result of the attestation is that the firmware gets the private key, basically the state of the VTPM loaded in it. So the only way for it to obtain the key is to pass the attestation, which means that whenever we see that there is a VTPM with a certain private key, we trust that it passed the attestation. In this case, we trust Microsoft as an organization, right, that they have this established. This is not happening on the host, and we trust them on that, right? Also, not Microsoft, but I've heard that various cloud providers are working on something which is going to be called like bring your own firmware, where you would be able to come with your own OVMF binaries there. But then again, you will need to build something like an attestation for your firmware, right? The firmware will load, talk to the server, say, hey, I'm good, I can prove that I'm good, right? Please give me some private state so I can continue executing. So this is like a tough question, right, with firmware, but getting there. And cloud providers are actually interested in making these confidential VMs confidential, right? They're on your side. They don't want to have access to your data because it helps them a lot to say, we can never get to your data. You know, you can use our infrastructure, pay us, but we have no responsibilities. Go ahead. Yes, there are. Yes, the question is, what about other non-x86 architectures, namely IBM System Z? Yes, they do have second generation of their something. I personally haven't looked much at how they do things. Although, like, we just had KVM forum and I chatted with them, and they do something very similar to UKI. They just don't call it UKI. And they were asking me, how can we get in? I just like start calling your thing UKI, because what you're doing is already like a unified kernel, and you're done. Right. So there is also this confidential, I forgot the name, in the ARM world, which is coming in like ARM v9 specification, right? So yeah, it's not exclusive to x86, and namely like systemd stuff we can now use to build UKI for both x86 and ARM. At least that's what gets booted through UEFI, right? Yes, it's just that without all these confidential extensions, it's like a pointless exercise, right? So you're not going to do much. Thank you. Yeah, catch me.
All right, we're on. Okay, so hi everybody. I'm Timothée Ravier, and I'm from the Chorus team at Red Hat.
I'm Shireen Khoury, and I'm from Red Hat as well in the customer focus team.
Hello, I'm Alessandro from the multi-edge team in Red Hat.
And hello, I'm Christian. I'm on the OKD Streams team in the OpenShift org at Red Hat.
All right, so we're here to talk about how we're building Kubernetes distributions and doing that the cloud-native way using OKD, using pipelines, using Tecton pipelines. First, let's start with what's OKD. For those of you who don't know, it's a sister distribution of OpenShift, which is a Kubernetes distribution. And we're not just bundling Kubernetes. We're bringing a lot of things on top. So one of the main things that we bring with OKD is that we bring the operating system as well. So OKD is based on Fedora CoreOS. And so when you set up an OKD cluster, you set up everything at the same time. You set up the system, you set up Kubernetes, you set up the applications on top, the operators, all very nice things to make developing on top of Kubernetes much easier. And you manage the thing as a single entity, and you update your cluster, everything at the same time. You update the system as well when you update your cluster. So this is a very nice experience of a managed system coherent Kubernetes distribution. And that's the main thing about OKD. So OKD is a community project. It's, as always here, as everything here is open source. And so far, it's been based on Fedora CoreOS. So the core is essentially of OKD was the operating system, was Fedora CoreOS, which is a Linux distribution. It's based on Fedora. It's an official Fedora variant. And the main thing behind Fedora CoreOS is that we have automatic updates. So we try and bring new content, updates, fixes, security fixes, and new features all the time as they get inside Fedora, and you get them. The basis between the benefits underneath Fedora CoreOS is that you're using an immutable infrastructure. So you are doing provisioning via Ignition. You write a config. You want what you want to have on your system, and you, from the first boot, you get a system provisioning configured as you like with the thing, with your containers and your configuration, your containers. And that's what we've been using in OKD. Fedora CoreOS itself is available on a lot of platforms, a lot of architectures, a lot of cloud platforms. You get a list of here. I'm not going to repeat all of those. We have almost support for 4 architectures right now, so x86 of course, AR64, S390X, and PowerPC coming real soon. So let's take a quick step back and look at the enterprise Linux ecosystem. So if you look at the distribution that we have Fedora, which is upstream, which is changing rapidly, which has a lot of new features getting in, new changes, experiments sometimes, things that may or may not work, all of those kind of things. And this is where the community experiments and do things. It's where we learn new code, we learn new software, we learn new features. And that's Fedora. Then we get now into things into Center Stream, which is a shared space, which is where we want to try and define where the next version of enterprise software, enterprise Linux is going to go, which feature do we actually want to have there, which changes, etc. And then finally, you've got like the Red Hat product, Red Hat Enterprise Linux, and all the other variants, which is product, so it's something made by Red Hat and sold. And so, but what about CoreOS then? Where does all of this, where does all of our Fedora CoreOS, Red Hat CoreOS edition fit here in the picture? And so far we had only 2. We had Fedora CoreOS, which is based on Fedora, as it said. We had the RHEL CoreOS, which is based on RHEL, which is part of OpenShift. And we are now introducing a third one, which is CentOS Stream CoreOS, which is the version in the middle. So it's keeping the same idea, keeping the idea of having a minimal operating systems with just what's needed, the container stacks, the what's needing for Kubernetes, and putting that on top of CentOS Stream. So the ecosystem looks like that right now, which is like we get Fedora-CoreOS, the version specifically for running containers on top of Fedora, the one CentOS Stream CoreOS, which is based on CentOS Stream, and the final Red Hat Enterprise Linux CoreOS for OpenShift.
So OKD on FCOS has existed for, thank you, a couple of years now. And basically, Fedora CoreOS is 2 to 3 years ahead of RHEL CoreOS. And that leads to some situations sometimes where features land in FCOS and they make some OKD components break. And the maintainers of those OKD and OpenShift components don't really have the bandwidth to look at it. And basically, that's really sad. So if we look at OKD on SCOS, it's a win-win situation because our SCOS is going to be about 6 months ahead of RHEL CoreOS. And so basically, the components team really benefit from running their components on SCOS because they get a really early signal of what's going to happen when they land the new RHEL CoreOS for OpenShift. And we are living in really interesting times for this because infrastructure changes and features are coming really very quickly. And we want that as early as possible in the software. So that means that we need to deliver the OS now faster. This wasn't the case a few years ago. If you think about the last version, the OpenShift version 4.13, we've delivered this nearly in the same time frame as RHEL 9. And that was a first time. We're still learning. And that's where this team, OKD Streams, comes in. We here and other colleagues are not from the same team. We just gather together to make this OKD Streams. Our goal is not to build OKD. Our goal is to build the tools that would be needed by the community to build OKD. And that means OKD from the grounds up. So starting from the CoreOS, any flavor of CoreOS, whether it's CentOS or something else you want to test, to the OKD components, release, and later operators that run on OKD. Why not also go crazy and test changing some component of OKD by something of your own to experiment? So when we started on this journey of building these tools, we had an easy option, which was to use Prow CI. I don't need to introduce Prow CI to you. It's beyond needing any pitches. It's developer-centric, and the problem with it was that the Prow CI specific that we use for building OKD on FCOS is not accessible to the community. And that's why we chose to switch to Tekton. Tekton has, firstly, is cloud native, and secondly, it has a very, very powerful and active community around it. You can see it just by looking at the quantity of tasks that are ready for you to use in the Tekton hub. And also, since it's cloud native, all of these resources that you usually use, like secrets, volumes, config maps, they are ready for you to use, and they come with really low learning curve to us. And that's why we switched to it. So here I'm going to introduce two of the pipelines that we have. The first one here that we're seeing is the one that builds the CoreOS. It can run on any Kubernetes distribution, so including Kind, if you want to. All you need to do is clone the repo that you have on the bottom there, use Customize to apply everything to the cluster, install Tekton controller, and you have everything ready to build CoreOS. Most of the tasks that you see here are based on a container that we call the COSA container, the CoreOS assembler container. It's basically just a toolkit around building CoreOSs. So it comes with everything that you need, any wrapper around RPMOS 3, building, testing, building extensions. So we build extensions to the live ISO, to bare metal, to OpenStack, and that's available for you to use on S3. The next pipeline that we see here is the pipeline that we use to release OKD. Before we get into that, today, so far, the OKD components are still built in the PRAO system, but Alessandro is actively working with the other colleagues as well to deliver an OKD payload pipeline, so you'll soon be able to build those components also in Tekton. So this pipeline is fairly easy. It just queries the release controller on the PRAO CI cluster to get the tag and digest of a valid and verified release, and basically signs the release, mirrors the components, generates all the release notes and stuff that we need, and updates the channels so that you can as well upgrade your clusters. And next, I'm going to hand it off to Alessandro.
Thanks. Okay, so what Shireen introduced so far are the pipelines that we use to build CentOS CoreOS, the base OS. We are working on the pipeline to build the payload itself. And well, what triggers the pipelines today? We are still using Tekton as a base, and Tekton provides an extension controller with a few custom resources under the group triggers.tekton.dev, for which you can be able to essentially define in an event-based fashion how to trigger your pipelines. The main resources are the event listeners and the triggers. The event listeners will essentially expose an HTTP handler where the event producer can send requests with a payload and the information about what the event is and how it is made of. And triggers instead defines what we want to do based on that event. They are made of 3 other resources, which are trigger bindings, trigger templates, and interceptors. Trigger bindings allows you to map essentially the data from the request payload to the pipeline run that we are going to create. Trigger templates defines the pipeline runs, the task runs, the Tekton objects that you want to create. And the interceptors are a more active way for defining ways to either map or filter whether to run or not your pipeline runs. Events can be whatever. They can be events from a Git repository. They can be events like periodics. What we currently do is to run essentially a periodic job for building the base OS. And what we want to go to in the next steps is to leverage these triggers in order to also support multi-arch images that the multi-arch images for CentOS CoreOS. What's the problem there? Actually, what you can do now is to run the pipelines within any cluster architecture. There is no specific, no architecture-specific bindings that would avoid you from running the pipeline into another architecture. Let's say at least for AMD64 and ARM64 at first. The SCOS manifest in the OpenShift-OS repository from which we get the manifest, the configuration for CentOS CoreOS, have all, if any, possible architecture-specific information that you need to build for that specific architecture. And what you get from the pipelines are separate cloud boot images, one for each architecture, essentially, and for cloud provider, or ISOs for bare metal, and separate container native images, which are single arch container images. What we want to do is to have a unique manifest list container native image. And we want to achieve this by using triggers because Tekton does not provide any way to add node selectors, node affinities and select which nodes you should use in your pipeline to run your task run. You can do that only at the level of pipeline runs or task runs, which are the instances of the abstract pipeline that Shireen described so far. And so the simple way is to just run two times, let's say, for two architectures, the pipeline from the cron trigger that I was talking before. But at that time, you continuously get single arch container images that you want to compose into a manifest list. We want to leverage an interceptor and another event listener, essentially, by feeding a config map each time build is successful for a given architecture, storing this into an array or let's say into an array, and trigger the event listener so that the interceptor defined within it can understand whether it's time to build and compose the manifest list. When it's time, so when all the architecture images, the single architecture images have been built, the compose manifest list pipeline will trigger and compose the manifest list from the single arch ones. Still talking about next steps, we are working on having on introducing the Fedora CoreOS layering approach into CentOS Stream CoreOS, because as of now, what you get when you get CentOS Stream CoreOS 9 is an OKD-specific CentOS Stream CoreOS 9 that has packages and configurations within it which are specific to OKD. What we want to go to is a model for which we become, let's say, first-tier providers of the CentOS Stream CoreOS base images, and we also consume at the OKD level, let's say, these base images by using by extending them through a container file like the one that you see in the bottom of this slide, and adding layers, packages, configuration, anything which is specific to OKD, and to be then published with the OKD release pipeline that we were discussing before. This means that we get to a model for which we have this base image, and any second-tier provider can consume it and do whatever they want with it. You can essentially leverage any of the services offered by RPM-OS3 with the robustness given by the CentOS Stream repositories, and deliver them to the users using the container registries as transport mechanism. We are, as Shane was saying before, we are doing all of this work to be cloud native, to be Kubernetes native, and if you want to try out our pipelines, you can run them locally into any kind of Kubernetes clusters, for example, on kind. What we do usually is to, at production grade level, is to run it into hosts provided by the MOC Alliance in a collaboration that Christian will now introduce.
Yeah, so we have our build farm on the MOC Alliance, which is the Mass Open Cloud, or Massachusetts Open Cloud Alliance. massopen.cloud is their website. And we have started essentially a little joint venture, a collaboration with them from the OKD working group, the CentOS Stream Cloud SIG, or the CentOS Cloud SIG, the OKD Streams team within OpenShift, and then the MOC Alliance. And the MOC Alliance is a research-focused cloud, an educational-focused cloud. So what they essentially provide is infrastructure for their students. It's a group of university and other research-related projects that make up this alliance. And they use it for a whole lot of things. And their main thing is providing the infrastructure for their students, their folks to run things on experiments or anything really. And they essentially approached us needing the ability to spin up OKD clusters on their infrastructure on demand. So their students could spin up a cluster very quickly. And we've been working on enabling this. Oh, I hope you've been hearing me. We've been working on enabling this. And really, they were donated, I think, about 2,000 servers, and they racked them up somewhere, and turned on the power and gave us an IP range, essentially, to go crazy and enable this thing. And under the hood, what they did is they put an OpenStack-like API, it's called ESI, Elastic Secure Infrastructure, on top of their bare metal pools to manage those bare metal machines. So what we've ended up is essentially implementing a new platform for the OpenShift installer. We are actually aiming at using the agent-based installer to do this, which is kind of the new way of installing OpenShift on really any kind of platform, and specifically on bare metal platforms. So they provide us with the bare metal infrastructure, with an on-demand API that we can provision nodes with, and then it's essentially our task to run the OKD installer and spin up a cluster. And we've been, not only have we enabled this platform, we have also been given a build farm cluster to use ourselves. So essentially, we are now homed on the Mass Open Cloud. Our cluster was actually down last week for maintenance, and it's brand new, so we haven't configured it properly with everything. But I think we're almost there again, so build infrastructure is almost up again. And we'll essentially use that as our official build farm for the CentOS Stream CoreOS artifacts, which is the OS tree native container image, which is the OS tree shipped as a container image. It includes the kernel and everything, but you can actually manipulate it and change it like a container. And we just saw that earlier on this slide, the CoreOS layering. So you import the OS tree with a from directive here, and then you run RPM OS tree within the container, and that spits out another OS tree native container image, which you can also run as a container, or you can actually tell RPM OS tree to rebase your whole operating system to that OS tree that was shipped within the container image. So lots of interesting stuff. We are now part of the MOC Alliance with CentOS Stream and OKD. And really, not only our build farm is going to be there, there's also going to be a secondary build farm or cluster for OKD working group members. So anyone who's participating in the OKD working group and has some experiments to run, they'll be able to request a namespace on that secondary build farm cluster. And then even more importantly, the ephemeral clusters, which is end-to-end testing. We'll be able to run end-to-end tests on that platform. And also, obviously, since they're ephemerally or available on demand, that's also what the MOC university students will use, spinning up a cluster and then having it run for as long as they need it for their project, and then tearing it down again. So to give you an entire picture of the whole cake, it's all just pieces of cake here, multiple layers. So the base layer, the infrastructure, is Massachusetts Open Cloud and OpenStack. It's not a full OpenStack thing. It's an OpenStack API that actually manages bare metal nodes. Then we use OKD's agent-based installer to set up clusters. On top of those clusters, and especially for our build farms, we use Git SecOps with Argo CD, and that runs our Tecton pipelines. And yeah, that's what we run. That's essentially our product, what we own as the OKD Streams team. We make the OKD pipelines that produces the OKD artifacts. We don't necessarily own the operating systems therein. We just own the build system, and we want to really enable a kind of self-service. It must be super easy for anyone to replicate a build or to change something up, replace an RPM or add additional RPMs, and run an RPM OS tree compose yourself. And this is with CoreOS Assembler, and this is what our pipeline does. So you can create your own RPM OS tree based operating system yourself, or create a derivation of Fedora CoreOS or CentOS Stream CoreOS, or even if you're a paying Red Hat customer, RHEL CoreOS. So it's a really flexible and powerful tool, a toolkit really, and we're looking forward to you using it, giving us feedback, and telling us what's not great yet, what needs to change, and also obviously we'd like to hear what works well, what you like. So this is essentially the call for action. If you're a developer, you might want to try OKD on top of SCOS, CentOS Stream Core OS, because it's more stable than the Fedora variant, just because, as Shirin mentioned, the kernel isn't so far ahead as the Fedora one. For staging, if you already have an OpenShift cluster on your in your company and you want to kind of run a preview of what's going to come to OpenShift in 6 months or so, you can use a CentOS Stream cluster for that. And then obviously for labs, for any kind of experiments, the students, educational projects, open source community projects. This is what we want to see use OKD, really. So with that, I think we're through and we can move to questions. So thank you very much. Any questions? Not so shy. There's a question.
So, maybe just a question. What was the motivation behind, like, why you decided to go like physical system and you don't like try to be more sustainable in the way that you go to public cloud or whatever cloud? So you like, build your service and then like break it down. Let's try to be, let's say, greener.
Yeah, I think there are probably multiple. Oh yeah. Why did we choose to go with a bare metal-based infrastructure to set this up instead of a public cloud? And I think the reason is that we just have a really good connection to the MOC Alliance. They need us to implement this, and we need them for the free infrastructure, right? There's no, they don't charge us for using this. It's a pro quo essentially, and we just like if there's a public cloud operator who would give us those resources and say, look, you don't have to pay for it, just do the work, we'd probably do that too. But this was just the first kind of joint project that we did in this way. And since we're from the community side of OpenShift, and MOC Alliance is an educational research project, that was just a perfect fit. Yeah. So Argo CD. Oh yeah. Question was why do we have Tecton on top of Argo CD? Why isn't it the same layer? Is that right? So essentially, Tecton, the Argo CD GitOps, which is added as a GitHub app to the repository, it watches the contents of our GitOps repository and applies anything. It can be a Tecton resource or any other kind of resources on the cluster it's supposed to land on. So really the Argo CD is a more agnostic controller for resources in a GitOpsy way. So it's not just, but we do control the Tecton pipeline runs through Argo in that way.
There's a question online on the Matrix channel from Joel. He's asking, can I use this to deploy microservices I'm working on?
You can, the question is, can I use this to deploy microservices? My own microservices, right? And well, the question, yes, you will be in the future. We are, as I mentioned, still ramping up our build farms and the community cluster on MOC. But once we have the MOC community cluster up, you'll be able, as a OKD working group member or an interested party who presents themselves to the OKD working group and says hello there, you'll be able to request a namespace and then use that to run your experiments. We don't have any rules yet on how long these things can run and how compute heavy they can be. I guess if it's abused at some point, we'll we'll kick people out again, but we don't have any tenants yet, and we're looking forward to our first tenants. And that's essentially, if they have something they want to prove out, make a proof of concept, or run an experiment, the community built cluster would be the place. Yes.
Maybe one more. How many architectures are you building?
How many architectures are we building? Currently, we only build x86 because we don't have access to ARM builders. We don't do virtualized builds, so it's all native builds, and we don't have access to ARM machines at the moment. And that is something we've been wanting to do for a while now, add multi-arch builds, add ARM as a second architecture. It's hopefully coming soon, but we still need to find an ARM builder to actually run those.
Yeah, but maybe because this is like quite powerful part, so maybe you could run like put the cable layer and build maybe just.
Yeah, we could definitely do that. It's just we have essentially decided not to pursue virtualized builds, since all of our productized downstream builds are also native builds, and we just don't want to do something that essentially we can't use downstream. So all of this is also meant as inspiration for our colleagues within the OpenShift org to show them that you can use these tools to build OpenShift or OKD instead of the ones we have internally. It's not meant to replace anything, but it's meant to kind of show folks to, yes, we can change the build system and see progress there, move forward. And with the Tekton tasks, it's just one reason why we chose Tekton is because it's so easy to share these tasks. There's Tekton bundles or catalogs that you can reference, and so the actual task YAML doesn't have to live in a local repository. You can just reference it, and the actual task definition or pipeline definition can live somewhere else. So that's really, really flexible. Any other questions? All right, I think, thank you again for having us. Yeah.
Now? Okay. Hi. Everyone is after lunch. So we are going to walk you through today about hot plugs in virtual machines. My name is Eddie. I work for Red Hat on a project called KubeVirt, and this is Andrea. He's also from Red Hat. He's working on a project called LiveVirt. Who knows? Anyone heard about LiveVirt? Oh, everyone. You're famous. Anyone heard about KubeVirt? Oh, so if you know KubeVirt, then you also know Kubernetes, so we are good. Okay, so a little bit of background and context. At the beginning, we just had a virtual machine, and life was really, really simple, right? We just had to manage that one. Then we had many virtual machines on many nodes, and it was getting difficult, so we invented management. And we had to manage a virtual machine, and our projects that we already, maybe you know, like Ovirt and OpenStack that manages virtual machines and others. And then came the containers, which are a soft virtual machine. So it's lighter and nicer, and you can run just application inside of them. And it had the same phenomenon there. We had a lot of containers, so we had to manage them as well. So then came the big players and invented Kubernetes. And Kubernetes started to manage pods, which are the lowest entity there. And in the pods, they are containing many containers, something like that. So you can consider them as containers as well. So there was just a specific implementation. And then came KubeVirt and said, why, if we can manage the ecosystem of managing Kubernetes very similar to the ecosystem of managing virtual machines, so let's put VMs in that ecosystem and put them in pods, which sounds ridiculous, and combine them both. So we'll use all the scheduling, all the nice features of management that we had on pods and the ecosystem to do the same thing for VMs. So this is KubeVirt. And from then on, we will try to go into the hot plug thing. But first, we'll just expand it. In order to define a virtual machine, in KubeVirt, we just define a manifest, which is like a specification. And the whole system creates for us the virtual machine inside the pod. It is powered as usual. I mean, all the OpenStack and Ovirt in the past, and KubeVirt as well, is implementing virtual machine also using LiveVirt and QEMU, because you already know what it means. More or less, if you look at this slide here, we have three levels of abstraction. So we have the manifest. This is how KubeVirt looks at the virtual machine. Then we have LiveVirt, which manages the life cycle, and it's an abstraction API to QEMU. And we have QEMU itself, which it's actually the application that emulates for us the virtual machine. This is how a manifest or virtual machine manifest looks like in KubeVirt. I will not get into the details. It's just an example here. It's declarative, and that's the whole point of what Kubernetes is. So we got to the hot plug thing. So in previously, like if I take Ovirt as an example, we had their support for hot plugs. Do you know why we needed hot plugs in the first place? Anyone? Yes?
For drives?
For?
For interfaces?
No, not for. Why? Why do we even need it?
To implement C-side driver, for example.
Okay, but why is it useful for someone to just hot plug something in? like in the middle of, like if you take a physical machine and put a PCI inside of it while it is running. Yes. So I think one of the most use cases that someone wants to do a hot plug in general is to, in networking, for example, you just want to connect to some other network on the fly, or you want to change some network parameters that you cannot do it outside the VM, like in the external network. That's one option. Or maybe you want to add more disks to your virtual machine, and all of this operation that you don't want to disturb the application that runs in your guest. You don't want to shut down the VM and then power it on again, so you want to do it on the fly. It also allows you to scale things later. Like you could start with something small, and then maybe you find out that you need more things, like more disks, more storage. So you want to hot plug things in to get these features. This is not limited to interfaces or disks. It can be CPUs. It can be anything. So what are our challenges with hot plugs? There are a lot. So it starts with Kubernetes itself. So Kubernetes itself gives us, if we are talking about devices like PCI devices, for example, the easiest one that I can give is SRV. So if I want to push in an SRV device inside, I need to first move it inside the pod, right? So the VM can consume it. So in Kubernetes, there is a device plugin, a component that allows to specify a specific device and ask him to move it inside the pod so it can be consumed. And in networking, for examle, we also have another part. It's the CNI. The CNI goes into the pod and the pod network namespace and can configure it with all the needed tweaks to have the interface of the network inside the pod and for it to access the node. But this is a Kubernetes thing. Device plugin can be only done at the startup of the pod. You cannot do it while it is running. Like once the pod is already active, you cannot use the device plugin anymore. And the CNI recently, in the last, I think, half a year or a year, there is now, using Multus, we can we can hot plug things into the pod while it is running. So this is a new thing, but it is hot pluggable. We have a way to overcome the device plugin problem, like with SRV, for example. In KubeVirt, what we do is we unplug. We need migration. So when we do migration in KubeVirt, the destination pod is created, and we can do everything there. So the device plugin can work on the target node. So what we do in KubeVirt for SRV, for example, we unplug everything in the source, all the SRV interfaces, devices, and plug them on the target afterwards. So it's kind of workaround in this cold plug using migration. Now the KubeVirt challenge. I'm not going to get into this mess here, but KubeVirt has a lot of components, and if you want to do one thing there, you will need to most likely synchronize them all. So, for example, here the request comes to a component called the Virt API, and from there it goes to the manifest, and Virt controllers reconcile this manifest and ask the Virt handler to start doing some privileged stuff on the node itself. For example, the Virt handler needs to go inside the Virt launcher that you see inside the pod and do the networking stuff. And then it reaches the Virt launcher, which is the KubeVirt representative in the pod that does all kinds of things. And there, the continuation of our talk today, there the domain, it touches the domain configuration. It talks with libvirt in order to do whatever is needed. We are going to talk mainly on this part here from now on. Andrea will we'll continue that. So, yes.
Quick switch.
Quick. It will not be quick, probably.
All right. So, can you hear me fine? Yes, good. So, when it comes to hot plug at the liver level, by the way, if you have any questions, raise your hand. We'll have time for questions later as well. So, the problem when it gets to liver, the problem with PCI hot plug is that it requires planning. This is the case for the Q35 machine type, which is the default in KubeVirt and the recommended one. You cannot just hot plug devices just willy-nilly. You need to prepare for it in advance. So the way that this works is that you have your machine, and so the part like in, which one is it? This part is we can consider part of the machine, and it cannot be, anything here cannot be hot plugged. So you have your root bus. It's a PCI bus. It cannot be hot plugged. You can plug devices into it, but the devices will also be considered as integrated devices, and so you will not be able to hot plug them or hot unplug them. In order to have hot plug working, what you need to do is you need to add some additional PCI controllers called root ports. You plug those into the root bus, and those cannot be unplugged or plugged, but the devices connected to them can. And at that point, you have hot plug, which is what you want. So here we have two devices that can be potentially unplugged at runtime. If you want to have the ability to expand your virtual machine later down the line, you just create a few spare ones, as many as you need, and then you can do hot plug. When it comes to libvirt and how it facilitates the hot plug on Q35, it is by doing a bunch of stuff for you. So if you have this XML, which is a very simple XML that describes like a single network interface, you can take this and provide it to libvirt, and libvirt will add some other XML to it. All of the stuff in yellow is stuff that libvirt will add automatically. It's a bit complicated, so we're going to go through it like step by step. So the first controller is PCI, the root bus that we were talking about in blue. On top of that, you have one root port, and then you have your device. And so all of the stuff with address type, all of that is just information that libvirt needs to record the relationship between the various devices and controllers, and so basically the vertical lines. So this happens automatically. You provide the device, you get the PCI controllers. So that means that hot plug works. Easy, right? No, of course it's not the case. There is a problem with this, and can anyone guess? Did anyone spot the problem?
Amount of slots you can plug in?
Go on.
There is limited amount of slots which you can use to plug devices in.
Right, close. So yeah, right. I'm going to repeat the question. He said that there's a limited amount of slots that you can hot plug, that you can use for hot plug. Yes, it is correct. Like more precisely, or like more to the point, is that libvirt can only automatically add PCI controllers for devices that it knows about. And the devices that you are going to hot plug, by definition, libvirt cannot know about ahead of time. So it cannot automatically add the controllers for that. That's why I'm saying that you need planning. So the question is, how do we solve this? How do we manage to convince libvirt to give us all of this PCI controller goodness without it knowing the devices in advance? The solution that we have come up with is that of using placeholder devices. So we'll have an example here. This is a standard, like very simple KubeVirt virtual machine with just one single network interface. And this will result in KubeVirt generating this XML, which is like same as we've seen before. KubeVirt will also add another interface that is marked as a placeholder, like you can see here, placeholder, right? So when this definition is fed into libvirt, the result is that libvirt will add a bunch of controllers, right? So resulting in this PCI topology. And you can see that there are 2 root ports because libvirt realizes that it needs room for 2 devices. At this point, we take this definition that libvirt has augmented with additional information, and we remove the placeholder. But we don't touch any of the PCI controllers. So now we have 1 empty slot, which is the goal that we had in mind. So this virtual machine can now be booted, and it has room for plugging in 1 device at runtime. We have decided that 4 is the magic number. Like, you're going to get 4. There is no particular meaning behind this number. It's just a small number that we feel will be useful to people without being overwhelming, and we can change it later. So for now, it's 4. This is what we have implemented today in KubeVirt. Before going with this route, we went through a number of approaches that we consider and ultimately decided not to follow. So the first one was to ask the user to manage the controllers explicitly, which is what libvirt users have to do. That is fine for libvirt, where you need to have very detailed control of the PCI topology of your virtual machine. But KubeVirt is a much higher level tool, and so we didn't feel like it would be asking too much of users. Users of KubeVirt should just be concerned about how many network devices they want, not whether those are going to be plugged in whatever kind of controller and all of the requirements that come with it. So we rejected this idea pretty quickly. Another approach that we consider is the use of the PCI bridge controller, which is a PCI controller that looks a bit like the root port, but it has a number of slots in it, and all of them are capable of hot plug. So it sounds like it would be a great solution for this problem. However, the slots on a PCI bridge are not PCI Express. They're conventional PCI, and libvirt will not use them by default on a Q35 machine type. You can convince libvirt to use them, but it basically requires you allocating all of the addresses manually. So KubeVirt would have to get into the business of picking the PCI addresses for all of the devices, which is extremely complicated. KubeVirt, understandably, doesn't want to get into the business of doing that when libvirt is already has all of this logic implemented. And plus the devices would not show up as PCI Express inside the guest. So there's a number of drawbacks. We rejected this option as well. Another option that we consider was to, instead of just saying 4, just to allowing the user to specify exactly how many placeholder they wanted to have. This is actually what we implemented at first, and then we decided that most users would not have to worry about this. We didn't want them to need to worry about it. So we scrapped the interface and just hard-coded 4. This is up for debate. Maybe we will change our minds. We will see. In terms of future work, this has been merged, as I mentioned. So this works today in KubeVirt. One thing that we could do in the future is to make this general concept of using placeholder devices to create PCI slots for hot plug could be extended to other kinds of PCI devices. The first example that comes to mind is disks. It's the most obvious one. Today, KubeVirt implements hot plug for disks. The way they do it is through the use of the VirtIO SCSI controller, which works fine. But there are some drawbacks to it, as well as some advantages. So it's kind of a toss-up. Thank you. So maybe we could have these extended to disks and make it possible for the user to choose to use VirtIO block instead of VirtIO SCSI. it's interesting. We will explore it and see what comes out of it. Another idea is to use a much larger number of PCI slots, like 32, to sort of match what you would get out of the box on the PC machine type. This sounds like a good idea. There are, however, some drawbacks in terms of resource usage. Every time you add a PCI controller to your virtual machine, you affect negatively the memory usage, the boot time for the guest operating system. So maybe 4 is enough and 32 would be too much. But maybe the overhead is not big enough that it matters in the context of KubeVirt. And like a number like 32 would give enough headroom that most people will never have to worry about it, while not having such a big impact on performance. So it could be a good development. Again, we're going to explore this and see what comes out of it. And this is the end of the presentation. So any questions? So the question is about memory ballooning. Memory ballooning is a completely different topic because the memory balloon is a PCI device, but it's a device that you provide to the virtual machine, and then the ballooning doesn't happen through plugging in and plugging out PCI devices. You just inflate and deflate the balloon. So you can create the balloon when you define the machine, and it will just be there throughout the lifetime of the virtual machine as you inflate it and deflate it. So you have to do 0 of these shenanigans. Yes, please.
Can you change the number of PCI slots by using migration?
So the question is, can you change the number of PCI slots when you do migrations? Not as implemented today. Theoretically, you could do it. You could have migration hook that changes but then you get pretty deep into the inner workings of PCI topology, and you get a very low level. So you're basically on your own, kind of. But you can do it.
Is it limitation of QVirt or GVirt?
Question, is it a limitation of QVirt or libvirt? This is a limitation, I believe, of the PCI spec. You cannot hot plug root ports at the QEMU level. And as far as I understand, this is because of the way PCI works. The number of PCI controllers is detected by the guest operating system at boot time. And once you are inside the guest operating system, it is capable of detecting that new devices are attached to an existing controller, but it cannot figure out that there is a new controller coming in. So PCI spec, as far as I could be wrong about this. I'm not 100% sure, but I think it is correct.
What about CPU hot plug?
What about CPU hot plug? Again, like ballooning, completely different topic, because the CPUs are not handled by plugging in PCI devices. We are aware of some work that is happening, right, with regards to enabling CPU hot plug in KubeVirt. So we know that it's happening, but neither of us knows the details. So I'm sorry, but you can search, probably find the open merge request or pull request, or maybe it's been merged already. I don't know. It's merged. Okay. Okay, so CPU hot plug is a thing, just not this thing. Yes?
What about making that PCI bridge PCI Express compliant?
What about making the PCI bridge PCI Express compliant? I think that was raised at some point as a, why don't we do that? I don't know the answer. There are various PCI controllers. I think that, okay, I'm probably misremembering the details, but I think the idea behind all of that was that PCI, the conventional PCI and PCI Express, although they share most of their name, are actually extremely different technologies. And so PCI is like a bus-based topology, whereas PCI Express is a like point-to-point topology, technology, okay? And so what you would get by having a PCI bridge that is PCI Express, it would ultimately be 32 PCI root ports in a row, and nothing more than that. So in that sense, this idea would be the idea of having 32 PCI root port in every virtual machine instead of 4, right? So in a sense, we're considering it. It's just different controller. Yes?
I guess all these limitations and how Black works for Liquid is not only limited to QBIR, but any other virtualizations.
So the question is whether these limitations are inherent to KubeVirt, or since they are in libvirt, they are shared by any virtualization option built on libvirt. And the answer is yes. They are shared by any virtualization solution built on libvirt and QEMU. And again, I think anything that uses PCI has this limitation, because it's not really an implementation problem in libvirt or in QEMU. In libvirt, we are exposing the limitation in QEMU, and my understanding is that QEMU is simply complying with the limitations of the spec. So as long as you're still on PCI, this is what you have to deal with. You got to plan ahead of time. I think there was a question there, yeah. The question is, how do you plug a new volume inside a running pod? And I'm not the good person to answer that, so I will pass it over to Ed. And not even Ed, so apologies. Like, he's a network guy, mostly.
You said you can do it in libvirt, and in libvirt, you can add new volumes to virtual machine.
Yeah, so we know it's possible to do it. We just don't know the details of it. Like, I know a bit how it works at the libvirt level, but not at the pod level. I'm sorry.
It's challenging more.
So the comment from Ed is that it's challenging.
There's no other question.
No? You want me?
No, I just, maybe you will translate it.
Sure.
Just repeat it.
Mm-hmm.
We have a hook inside KubeVirt that can change the domain XML, so the configuration of it. So if someone needs something very, very special, you can just use that hook.
Right. Right. So basically, as I was mentioning earlier with the PCI controllers, there's an escape hatch for all of this stuff. In KubeVirt, you can expose a domain. It's a migration hook. It's just for migration. It's just a sidecar. So you can do sort of arbitrary transformation to the libvirt XML, inject your own custom things. Of course, if you break something, you get to keep all of the pieces. So ideally, you will not need to do it, but the option is there in case you have no other options. All right, I think we might be good unless, last call. Any last minute questions? No, okay. Then thank you.
Okay, so hi everybody. I'm Arik Adas, and in this session we are going to see how volume populators are being used when migrating virtual machines, and we will try to answer the question that appears in this slide of whether volume populators fit also for virtual disks of virtual machines. A bit about myself. When I joined Red Hat, I started contributing to OVIRT. It's the upstream project of Rev, Red Hat Virtualization. Then I contributed to QVirt, the upstream of OpenShift virtualization and the successor of OVIRT. I had a short break from virtualization in which I worked on other OpenShift stuff. And in 2020, I switched back to working on OVIRT. And now I'm working on Forklift, which is the upstream of MTV migration toolkit for virtualization. Forklift is an extension to Kubernetes that enables users to migrate virtual machines from traditional legacy virtualization management systems to QVirt or OpenShift. In OpenShift 2.4, the available sources are vSphere, OVIRT, and OpenStack. And these days, we work on adding more sources, OVAs, virtual appliance files, as well as QVirt itself, in order to enable migration between QVirt deployments. Generally speaking, Forklift is targeted for mass migration. And in more details, the idea is to simplify the process of migrating virtual machines at scale to OpenShift with just few simple steps that are listed here. And let me show you how simple they really are. At the right-hand side of this slide, you see the Forklift UI, the new UI that is integrated within the OKD or OpenShift console. And the process of migration using this UI looks as follows. We need to define a source provider. In this slide, you see the complete form for defining vSphere as a source provider. If we migrate to a remote cluster, not the cluster that Forklift runs on, then we also need to define this cluster. But in this example, let's say that we migrate to the local cluster where Forklift runs, so we will skip the next step and get to the creation of the migration plan. So in this form, we need to specify general things like name, description, and also pick the source and target providers, as well as the target namespace that the virtual machines will be defined in within the target provider. Once we do that, we click Next, and we see a list of virtual machines that exist in the source provider, along with more information that users need to know before triggering the migration. We select the VMs that we want to migrate, and click Next. This takes us to the network mapping view, where we can easily map networks that exist in the source provider to networks that exist on the target provider. With a similar user interface, we also define the storage mapping that maps storage domains, devices, types, data stores, depending on the source, on the type of the source provider, to storage classes on the target OpenShift cluster. Once we do that, we will see our plan in the plans view, and we can simply start it by pressing the Start button. Once the migration is done, we will eventually see the migrated VMs in the target namespace within the target provider, and we can start using them. But what happens in between, during the migration itself? So if we migrate VMs that ran on a foreign hypervisor, not KVM, then we need to convert the disks. We convert their format, replace the drivers, replace guest tools, etc. And then we need to copy the rest of the data from the disk to the target storage. Then we need to change the configuration of the VM in order to adapt it to QVirt. In this session, we will focus on the first two steps of the conversion and copying of the disks. So that's about MTV. Now let's talk about the volume populators feature, which is a recent feature that landed in Kubernetes and OpenShift. And the purpose of this feature is to import data from remote sources to our cluster. I will demonstrate how it works with resources that were shared in a blog post that was written about this feature. On the left-hand side, we see an example of PVC. When looking at its spec, we see the first part of the volume populators feature, which is the data source ref. This allows us to point to another CR, in this case to a CR called example hello, of kind hello. And we can see this custom resource on the right-hand side of the slide. And specifically, we see that in its spec section, there are two fields, the file name that is set to example.txt, and file contents that contains hello world. When we try to use this PVC, for example, with the job that we see on the left-hand side, we can see at the bottom that it uses the example PVC that we saw before. And we also see that it runs a container that dumps the data of the example.txt file. We will see what we see on the right-hand side, that once the job is completed and we look at its logs, we will see the content that we saw in the spec of the CR, in this case, hello world. So this is from the functional point of view, right, what it does. But let's talk about how it's done. So when we post a PVC that refers to a CR, there is a controller that detects it, and this brings us to the second part of the volume populators feature, which is the library called lib_volume_populator that facilitates the implementation of such controllers. The controller detects the PVC, it reads the custom resource that is being referenced, and based on the data it takes from those two places, it creates a prime PVC, which is similar to the original PVC. And this PVC is used by a populator pod. The populator pod then writes the data into the PV that was allocated for us. Once that's done, the controller attaches the PV that we saw to the original PVC. And in our previous example, the populator wrote the content that we saw in the spec. And now that the PV is attached to the original PVC, the job was able to get access to that and dump it. In Forklift, we implemented two kinds of populators, one for Ovirt and the other one for OpenStack. We read the data from there and write it to the PV. And if this picture looks familiar to you, we had a similar design in older versions of Forklift, and also if you use qvirt along with data volumes that refer to remote sources, in both cases we use CDI, and with CDI we get a similar picture. The only difference is that the pod is named differently. It's called importer pod instead of populator pod, and the sources are a bit different. We don't have support for OpenStack, but we have for others. In this case, I added the vSphere to the slide. So it works similar, it looks similar, but let's talk a bit more about CDI. So CDI was the solution that was introduced in qvirt before volume populators were implemented to import data from remote sources. It is based on the data volume CRD. We can see a CR of data volume on the right-hand side, and we can see in its spec section that it connects to Ovirt because of the image.io section. And yes, as I said, CDI also supports other sources. You can find them in the documentation of CDI. Before Forklift 2.4, we used CDI in all migration flows. And in Forklift 2.4, the latest version, it was partially implemented with volume populators. So I said it looks the same from the diagram that we saw, but looking more into the details, we see that there is a trade-off between the two. In CDI, there is an extension to Kubernetes with the data volume CRD, while with volume populators, we get a solution that is integrated within Kubernetes. This data source ref section exists in all PVCs since Kubernetes 1.24. We talked about the naming of the pods that is different. Another point is multi-stage transfers which allows us to do what we call in forklift war migration, the ability to copy snapshots of the data periodically, so that when the user asks us, we can shut down the VM, copy just the remaining of the data that has not been copied yet, and start the workload on the target environment, and that way we minimize the downtime. So we have no support for this with volume populators. Next, when we want to add another source to CDI, we basically need to extend the code base with more logic that is written in Go to support this new source. While with volume populators, we have a pluggable design. We can add a plugin that runs a populator pod that basically can run anything inside, right, regardless of the language that it is written to. And it even allows us to leverage native tools that are provided by the source system. And lastly, CDI is integrated solution in QVirt, and it is tailored to virtual disks. I will talk about it a bit later. While volume populators are not yet there. There is a work in progress to integrate them into CDI, but yeah, it's not there, and there's no notion of virtual disks or virtual machines with volume populators. The reason we chose to go with volume populators is twofold. One, we wanted to leverage the pluggable design, and second, we wanted the ability to run native tools inside the populator pod. When we planned Forklift 2.4, we realized that in order to be able to deliver the feature of migration from OpenStack in time, we need to minimize the risk. And that also means to try to avoid changing CDI. So we looked at volume populators, but we also realized that it will take us some time until we get to the point that we can transfer data, because we first had to create the inventory, and that took time. So the way we approached it is by starting with a volume populator for Ovirt that replaced some of the functionality that we had before with CDI. And let's see how that works. So there is a controller in Forklift that posts three resources: a secret that holds the credentials and properties of the source provider, a CR called Ovirt volume populator, and the PVC that will hold the content of the virtual disk. Then another controller, populator controller, that is based on the lib volume populator library, creates the prime PVC and the populator pod as we saw before. And inside the pod, we run the command that we see below that uses Ovirt IMG, a native tool that is provided by Ovirt to interact with Ovirt Image.io to upload and download disks. And then we write them into the PV. The OpenStack volume populator works in a similar way. This time we post a CR that is called OpenStack volume populator. Again, the same controller creates the populator pod and the prime PVC. And this time the populator pod runs code that is written in Go. It uses the Gopher Cloud library in order to connect to OpenStack, get the data from there, and dump it to the PV. With these populators, we were able, let's start with Ovirt. With Ovirt, we were able to accelerate the time of the data transfers. In our testing, in some cases, we also reduced the execution time by half. So it was significant. We were able to introduce another feature of transferring the data over an insecure channel more easily because we didn't need to change CDI. And we were able to introduce an alternative implementation to the one we had with CDI, and now we can deprecate the relevant code in CDI. And even more importantly, when it comes to OpenStack, we were able to introduce this new functionality of migration from OpenStack in time without changing CDI, as I said, and really it works very similar to that functionality of Ovirt. Some challenges and insights that we saw in the process. So the first one was that we initially planned to use CDI to allocate the PVs. We planned to create a data volume with a source that is set to blank, and then the populator pod would kick in and copy the data to the DV that we get. And that didn't quite work. I mean, the populator pod started and wrote the data into the PV, but afterwards the data was written by the importer pod because it tried to give us a blank volume, right, like we asked for with the source equals to blank. So that didn't quite work, and we had to skip using data volume, but instead to post the PVCs directly. The problem with this approach is that we lost the logic that we have in CDI for this. First, CDI knows how to pick the right properties for the virtual disk in terms of volume mode, volume access modes, and we had to duplicate it. And also, when the PV is allocated on a file system, the file system itself has an overhead. So this gives less space for the virtual disk. So we need to take this into consideration and allocate more data than we need for the virtual disk itself. And this is also logic that we had to add to the core code of Forklift. Next, let's talk about progress reporting. VM migrations can take time, even a couple of hours. So it is important for us to reflect the progress of this operation. We tried several things. Our first approach was to make the populator pod update the CR, put the progress on the CR itself. The problem with this approach is that it required another service account in order to let the populator do that, and that complicated things for us. Another approach we tried is to push the updates from the populator pod to the populator controller. The problem with this approach was that we had to propagate the endpoint that the data will be sent to the populator pod, and that also complicated things for us and didn't quite work in all scenarios. So we didn't use this one, and we tried another approach of pulling the data from the populator pod to the populator controller. This approach that is similar to what CDI does, and we actually implemented it, in a similar way, works by running a metrics server inside the populator pod, and then the populator controller pulls the data from there, the progress as metrics. And that worked well for us. Next is dynamic volume provisioning. So when we played with our implementation, it worked nicely in our development environments. However, we got reports by QE that on testing environments, migrations sometimes fail. When we looked into it, we saw that it happens when the target storage class doesn't support dynamic volume provisioning, but only statically provisioned volumes. So we figured out that it's an issue in the library, in the lib volume populator library. And we reached out to the maintainers there to explain and to try to find a solution, but we didn't find a solution we agree on. And since it's not that common to have such storage classes, and since it's not that important for us, we rather chose to block using such storage classes when using flows that use populator pods. Next topic is the conversion of multi-volume disks. So a bit of a background. When we convert, and I said that the conversion applies when we migrate from a foreign hypervisor, in that case, we run virt-v2v that allocates a local overlay volume that is backed by a remote volume. virt-v2v then inspects the data of the disks and modifies it, as we talked about earlier. When the disk is composed of a single volume, it works well with volume populators. However, when we have disks that are backed by several volumes, then this design breaks because volume populators expect one PV per populator pod, right? That all the data will be written to a single PV, and in this case we need more than one, and we also need to specify the information about the source volumes, and this doesn't quite fit. So again, we reached out to the guys that work on the lib volume populator library. We filed a bug. We had some discussion. But again, we didn't agree on a solution for that. So our idea here, we have a plan to change the code base of the library in order to support this. But we need to play with this and see how it goes. When it comes to migrations to remote clusters that I mentioned before, in this case, we need to post the CR on the target cluster, right, that we migrate to. And the populator pod also runs there, so we need to track the progress that it reports. This raises two questions. One, who should deploy the CRDs to that remote cluster? And second, how do we get the progress from there? Which component should do it? Our first attempt was to let a controller that already runs in Forklift on the source cluster to create the CRDs and also to get the data. But it appeared to be more complicated than we expected because usually CRDs are deployed by operator, right? And we didn't want to duplicate this logic. And also when it comes to progress reporting, propagating them to another cluster can be challenging. So we chose to avoid this one and rather try to delegate this to CDI so that CDI that runs on the target remote cluster will deploy the CRDs and also track the progress there. And that's a work in progress. We work with the CDI team on this, and I hope that it will get in Forklift 2.5. And lastly, some more adaptations that we had to do to the lib volume populators library. Usually, we try to create as much as we can of the resources that are per migration on the target namespace. That is debugging, and it also allows us to set owner references to improve the cleanup code. The library doesn't do it, so we needed to patch it. We got feedback from the guys that work on the library that they chose not to do it because they wanted to hide the prime PVCs and the populator pods from users, but it's OK for us, right? We actually do want it. So that's something that we did. Another point is limiting the number of restarts of the populator pods. We don't wish it to keep retrying, right? We want, at some point, to say that the migration fails and to be able to inspect the logs more easily. So we limited the amounts of restarts of the populator pod to 3. Also related to the cleanup, we want to correlate resources that are per migration with the migration itself. And again, we needed to change the library in order to set this label. And last but not least, when it comes to VM migration, it might be important for users to select the network that the transfer will be done on. It can be because we want to isolate this from the data that is used by the VMs, by the other VMs. It might be because we want to use a better network, faster network. Either way, propagating the transfer to the populator pod also required modifications. So to sum up, when we look back at the original question of whether volume populators fit also for virtual disks, I would say that the answer is generally yes. It allowed us to implement the original things that we planned, the basic functionality. And we also work with the CDI team to integrate our populators and volume populators in general into CDI. So that's a good indication that the basics are there and it fits. But when it comes specifically to VM migration, in that case we see that it's not quite, it's not completely fit. We see this by the amount of changes that we had to do to the lib volume populator controller, and basically that made us eventually fork it and add the code to our code base. And also, it was challenging to get the more advanced functionality, the remote migrations that we said, the warm migrations, and also the conversion of multi-volume disks. So those are all things that we think they are possible, but they require an additional effort, and we work on those things these days. And yeah, that's all from my side. Now your turn. Questions? Yeah.
I didn't get the first part. You told that when volume populator is forked, it reattaching PVC from PV, then attaching it to another PVC. How in this case PV not get deleted?
The PV itself?
The PV itself, yeah.
I will repeat the question. The question is, how come that when the prime PVC allocates the PV, and then we say that at some point after the write is done, then the PV is reattached, is attached to the original PVC, how come that the PV is not removed in the process? So this is part of the logic of the lib volume populator itself. I'm not that familiar with the details, but it catches this point and it just changed the reference. So it's done before something is lost, right? It kicks in, do this change, and then we get it attached to the original PVC. Sure. Any other question? Okay, if not, then thank you, everyone.
Okay. All right. Hello, everyone, and welcome to this talk about FinOps and observability. As last time, I was first talking about this in November here in Brno, and it was also unpopular by the title FinOps. So this time, the same, which is cool. I'm first going to reflect a bit about the talk in November that I had about the FinOps, and then we will move on into some more technical details about the talk, about the presentation, actually. So this part was already on November, so I will go through it a little bit faster. So the whole engagement started when my friend Andy Thompson and I were engaged in a project with a large company that needed us to sort out their FinOps engagement. Back in the time, I was a DevOps engineer. I didn't have any actual FinOps experience. So Andy and I started exploring what FinOps is, what it means for a company, how we can do it properly, and all that stuff, you know. At the same time, they had the first task for us, and this is the biggest cost they experienced was related to EBS volumes. And everything is happening on AWS. And the overall money the company spent on a monthly level was anywhere between 5 and 7 million US dollars monthly. And big pile of that money went to EBS volumes. So we started exploring what is going on with EBS volumes as engineers. You know, we looked into the patterns of use cases, how teams are using EBS volumes, what they do with them, and all that stuff. But at the same time, as I said, we were exploring the FinOps, what FinOps is, how it is managed, how it is defined, and what should we do as now part of the FinOps team, DevOps/FinOps team. While working with them, that was really a great experience because we were able to see firsthand how engineers in this large company were struggling with the idea of being into the cloud and not being able to use the cloud in the way they wanted. The promise of the cloud is that you get your resources when you need them, how you need them, you set them the way you want them, and all that stuff. That wasn't happening for this enterprise because the enterprise had strict rules about how to use cloud resources, how to manage them, when to dispose them, and all that stuff. So that was frustrating for engineers. At the same time, we were, as a team, engaged in a lot of talks with the management, so we were able to tell that the management was struggling with similar issues. They were struggling with the ways to control engineers from spending money on the cloud. So it is like a clash. On one side, you've got engineers willing to do stuff in the cloud, experiment, and try out new things. And on the other side, you've got management, which is keen to control the spend, which is natural. So both approaches make sense. While preparing for the whole stuff and exploring EBS and exploring FinOps, obviously, FinOps.org is the place to go if you want to learn about FinOps. And this is the beautiful definition standing on the FinOps.org site, which is almost completely not accurate. So this is really nice when you are in the management and you want to explain how FinOps is the next big thing. So a lot of parts of the company working together towards the common goal of making the world a better place, using less money, and everyone is happy and everyone is collaborating and all that stuff. But in reality, what we have found that FinOps is, after some exploration, is this. So FinOps is purely about saving money in the cloud. The whole talk about changing the culture in an enterprise, so every engineer would think about the cost, did not happen. I, at least, didn't see it. I was on that project for 3 years. And the reason why I didn't see it was the miscommunication between the management and the engineering team. And that actually guided my colleague Andy and me into building a system that we hoped that would help facilitate this communication, because that was the biggest the biggest challenge and the biggest disappointment. On both sides, you've got people who are willing to do something good for the company, but it's just that they're talking different languages. They have different goals, and that was always the problem in this. So going back to engineering, and I will be, during this talk, jump a little bit on the engineering side of the things, and then on the management side of the things. So what you see here is a flat, simple model that we used to analyze what is going on with EBS volumes. So we said, like, okay, we want to rely on AWS giving us the data, so we need pricing from AWS. Then we would like some metrics about EBS, about how EBS is used. If you want to see if EBS volume is unused, or if you're not pushing any data towards the EBS, you are not using it maybe, and you want to support these claims with actual facts. So if you can pull metrics, and if you can prove to your engineering teams that there is no byte coming to or from the EBS volume for some amount of time, that should be good enough for them to comply that this EBS volume is actually unused. I mean, physically and actually unused. Also, there were all kinds of specific conditions in this enterprise, how you declare that something is used or not, or how something can be used or not. For instance, they had a lot of accounts in AWS which were not claimed as production account. They are not labeled as production account, but they were used as production account. How this happens is another story. Short story about that is that they would push a new service, they would find themselves a client, they wouldn't get the approval from the company to create a production account to support this client, but they had a client. The client wanted to pay. They asked the management. Management said, yes, onboard the client. They onboard the client on the development account, and they just continue rolling in new accounts, new clients, and new clients on this dev account. And at the end, you've got a dev account supporting production. And there are all kinds of things you would find when you dig deep into these accounts that were used. We had communication with around 400 different teams running all kinds of projects in this enterprise. So we had to come up with some kind of custom rules that would help us control the whole thing. On the other side, we would collect the data, apply some pricing, AWS pricing on them, we would apply some rules, and we would do some logic around that, and we were able to generate two types of results, and this was very important for us. The one type of result would go into engineering teams, which means that we would meet with the team and we would present the data. And we would say, this is what we have found about your EBS volume usage. This is the list of EBS volumes. These are the ones that are not used. These are the ones that are not used properly. And these are the ones that are optimized. Them you don't need to touch. And we would support all this with actual data. The teams would get back to us. We would get into all kinds of heated discussions around what is wrong with EBS volumes. You know, these stories like, we can't touch this EBS volume. Why? Well, a colleague of ours created that volume and left the company. And we don't know why this volume exists in the first place. And you would say, yes, there is no communication with that volume. There is no bytes going to or from that volume for 3 months. So maybe it's safe to delete it, or at least to snapshot it and delete it. But they would be reluctant because they would say, well, we've got contracts and we've got SLAs with customers, and we would rather continue paying for that volume even though we don't use it than risking some outage of service or something like that. So again, these are real life stories, not something that we read in books, how we do stuff. One fun fact, the management didn't like this approach. They preferred this. This is the same stuff, but a little bit with colors and different shapes, and it looks a little bit more modern, and this resonated well with the management. When we had to present to teams what we do, we would use this model. And engineering teams responded well. This is simple, this is, you know, very simple design. But when we went to talk with management, this was the one. Because then we could say, yes, this is something magically that happens, and then we process some data, and then we generate some results and all that stuff. Apart from the first report, that was a recommendation for engineers, we generated a second report that went to the management. And what we did is we presented some recommendations on the company level. These recommendations would be like this. There is an opportunity to save X amount of dollars per month if you would be willing to perform these, and these activities. We already conducted talks with the teams, and we already got their estimations on how much time would they need to implement the changes. So that usually would be, you know, like open the Terraform file, change something, apply changes, and that's it. But we went through the talk and we collected the data about how much would it take to perform these changes. So now we would prepare a report for the management, and we would say, if you want to save this amount of money, it is possible. You need to come up with resources for engineering teams to spend this amount of time to execute these changes. And now management actually had something to, you know, make a decision, enough data to make a decision. It was palpable. It was not tacit anymore. You could actually anticipate how much time you would need, how much effort you would need, and what kind of money you would save. So again, this was, and this is one of the, I love on these talks to present these guys. This is Niklaus Wirth. Niklaus Wirth is most famous by being the father of the Pascal programming language, but some of his work is much more than that. I personally like this plea for Lean Software paper that he wrote in 1995. It's a 5 pages paper that explains benefits of a simple design. You can find more modern books about this, like David Furley has this book, Modern Software Engineering, which is great talk about how you simplify the design, how you start from a simple thing, how you add stuff into this simple thing, and how it becomes more and more useful. The whole talk, the whole approach is don't try to be modern, don't try to be, you know, tech for tech, but try to build tech that would be actually useful, that would sort out or deal with some problem. So again, this is the influence of the guy. This is how we build the models. After this initial success of the approach, the company said, like, this is all, one of my friend liked to say, nice and dandy, but can you do it for some other resources? Like, we've got DynamoDBs, we've got RDS instances running around, we've got EC2 instances running around, and we have no idea how to save some money on these. And again, my apologies to all the people that are dealing with actual software that was built to generate metrics or to generate the observability in different definition scopes. This is a different kind of observability that we are doing. We are not getting so deep into how many processes are being run on certain instances and how much memory they use or how much processing power they use. This is a little bit different approach. We wanted to be in the middle between engineering and what can be good for the company. So we said, like, okay, if we are going to do this for another EC2 or DynamoDB, let's say, we would like to build a framework. We would like to build something that can be reusable, that we can extend, that we can just add new stuff into the play. So we would have an engine, and then we would just, well, you can say add plugins to this engine. So the engine would become aware of how to analyze DynamoDBs and all that stuff. So we started simple. One of the colleagues on the previous talks talked about ECS, and it is the simplest form of running containers on AWS that you can actually orchestrate a little bit. What we wanted to achieve now into technical stuff, what we wanted to achieve here is try to minimize the need for orchestration and increase the choreography. So we wanted a lot of independent services running around, not needed to be orchestrated because we wanted to avoid this. If it comes to orchestration, then we will deal with that. But until we have to, we would like to avoid it. So we said, like, okay, let's treat this as a microservices architecture. Let's put the analyzing engine for EBS in one container. Then we put another one into a second container, like that one would analyze DynamoDBs. The third one would analyze, I don't know, RDS instances and stuff like that. So we started adding more and more services following the same pattern. Every service would have a different model, but the model would contain same stuff, like get me AWS pricing, get me some metrics that I need to assess whether this information is useful for me or not, and some custom parameters like the stuff that I talked about, whether some account is production account, so I cannot really apply some of the rules on the production account. Again, bear in mind that metrics and observability in terms of, let's say, how Mitzi Tipsy is explaining observability is different than this. This is like a high-level observability, let's call it like that. We would rely on AWS to give us data. So what we did is we put these containers in place. Then we needed to somehow start them. We had an idea of running them every day, collecting the data, and once a month we would generate these reports that we would push to teams that are targeted for actual optimization and to the management so they could figure out whether they want to invest resources into optimizing the infrastructure and saving money eventually. So we said, like, since we don't have a lot of orchestration, let's do it simple. We created events that are timed. So we said, like, in the morning we will schedule these containers, they will spin up, do some stuff. It was serverless, it was Fargate enabled, so all that is fine. After that, we figured out that a lot of these containers would actually go and fetch prices from AWS. We would need some secrets to store them somewhere in the AWS. And then somewhere around this point, we started thinking like, okay, how about we make everything idempotent and serverless? That means that if we are going to build it, I can run it many times a day and generate the same result, so I wouldn't mess up with my previous data. That was idempotency. And then serverless, well, events, ECS, Fargate containers, and all that stuff still is serverless. So that was cool. Then we proceeded and we said, like, okay, we want to go through accounts and we want to analyze what is in these accounts. We need some permissions, we need some account roaming stuff that will go around. And around this point, we started thinking like, maybe this orchestration, microservices organization is not the most optimal one. Can we put aside the tool, the piece of code that would go through all these accounts and do this for us and just hand us the token and we continue doing it like that? And that is doable as well. In our case, once we put it in motion, it wasn't really good use of our time. We figured out that it was, even though it's elegant in the code way of things, in the architectural way of things, it wasn't really elegant in the ways of us having to maintain that. And we always had in mind that at some point we will hand over this work to the team that should continue to maintain this. So we wanted to keep it simple and follow this approach. So we said, like, no, every container will have its own engine that will roam through accounts, so we could separate them even more, so we could avoid the orchestration. That was another reason why we avoided this, because this would introduce some piece of orchestration, and we couldn't scale them in the same way. So we kept the isolation thing. And then we said, like, okay, since we want to maintain this serverless approach, let's write some of the data to the Aurora serverless. Now, still idempotent, the data written in the database is not going to be there longer than a day, because we don't need it longer than a day. So if I rerun the task, it would clean the data for the task, it would regenerate the data, and the data would be fresh for that run. So this is why we could keep the serverless approach. We needn't keep this data for I don't know how long, and that was fine. Also, obviously, something on AWS, you need to log stuff, you need to send information, and this is the final stuff. This is where we, at the end of the day, the only piece of orchestration that we had to introduce is once all the tasks finish, we would push the data into the S3 bucket through some reporting mechanism, and from that point on, the data would be picked up by some of the Power BI or Tableau tools. It would be invoked into the Snowflake. It would be reorganized or done something different with it. At that point, company said, okay, can this be used for something else? And this something else we didn't do because the contract was expiring, and they didn't want to go through with the whole idea. But the question was, can we use this approach to make company more advanced on the market? Like, how do you do this? Well, you make your company serverless or use more serverless stuff. This company used a lot of EC2 instances, a lot of monoliths running around. So if you want to be more modern company or more competitive company on the marketplace, you should follow from the tech side of things how we see it. You should approach the way you build software a little bit different. So this is the slide that we prepared for the management, actually, when we went on a meeting. And we said, like, OK, if the management would like to be innovative and competitive, and if the tech has a strategy how to support this, so that means I, as a company, want to be competitive. Cool. What the engineering stuff can do? Well, we can build serverless. Cool. So we've got two ifs. Then score teams by their current level of serverless adoption, and then finally, management needs to approve resources to re-engineer and re-architect and rewrite these applications. This is how it goes. And the final stuff is this. When we went on a meeting and we discussed with them and all that stuff, and you know what it turned out? The company was more keen saving money than becoming competitive, because the company was already dominant on the market. And their idea of being competitive on the market was based on, OK, if we can do it, you know, with not a lot of effort and create a bigger gap between us and the competitors, that was cool. But when you introduce to them the idea about how this works in engineering mind, like you tell us what you want, we propose how we can assist you in the journey, we give you the estimate how much time, resources, money, people we need to make this happen, and then you say, yes, we want to make it happen, and then you follow it through. And then you can support this approach using this tool to provide you with a proper analysis on how much teams are serverless, how much teams would be capable of follow through the whole stuff. And this is, for us, for all of you who are my age appropriately, let's say, you remember Hitchhiker's Guide to the Galaxy and the bubblefish. And it was all that in our heads. Like, you create a tool that is a good tool to communicate between engineers and management. They usually don't know how to communicate. I'm sure all of you have been in situations where you wanted to talk with the management, but it doesn't really go both ways. So us providing this tool felt like providing the bubblefish. On one side, we were able to explain to the management what can be achieved with certain amount of resources, and on the other side, we were able to provide the engineering teams with what needs to be done, what should be done, and why we need to do this. Unfortunately for us, they didn't go through with the second part of the idea of modernizing the approach and making something better with the whole stuff. But the first part was good enough. So the bubblefish, in our case, really worked for the first piece. And it was very much thanks to Nicholas for the whole idea about how to keep it simple and how to be. There is one thing I want to mention at the end. It's really tough to build a software that you believe will create the benefit for the company and not introduce some nice and flary technical things you can brag about, because we as engineers like to be proud of what we do. And if you're not using the latest grade, you didn't see Kubernetes in this presentation. You didn't see any, well, not any actually fancy stuff that we did. It was simple, plain engineering that we did that did some good for the company. But I need to say, it's not really easy to defend this approach when you go into the purely engineering audience. You would get all kinds of questions like, why didn't you reorganize your microservices in a different way? Why didn't you do this AWS service or that AWS service? And it's really hard to defend when you have to offer an explanation like this. Okay, we knew which team is going to continue doing this after us. We were there for a limited amount of time. We wanted to build an application that will have longevity, that will be able to continue operating after we are done, and that will be able to be successfully managed by the team that we give it to. So that influenced a lot of decisions that we made during the architectural phase of the stuff and all that. If you're building a product, if you're building a service that you want to commercially offer to someone else, that's a different thing. You're building it for yourself with a different goal in mind. This was made specially for this company with the idea of then being able to take over the product, the service from us and continue using it, and it saved really a lot of money. Well, it's not that difficult to save money when you have a company that spends like $5 to $7 million per month, but it was fine. It was cool. In the end, I think the last year went through like the company said, if they don't save us as a team, Andy and I, if they don't save more money than they cost, you don't have to pay for those two guys at all. And that was really easy sell on the management level. But I wanted to re-emphasize this one more time, and it is the end. If the company has a strategy, and if the company is able to communicate through the strategy, and if the company is able to stick with the strategy, then tech guys will follow. Otherwise, you will have all kinds of clashes between the management side of things and the engineering side of things. And this is it. And once again, thanks for Nicholas too, for his appearance. Okay, questions? Yes?
So you said you started as a DevOps engineer, and then you learned a bit about FinOps.
Yep.
But it seems to me you ended up working as a translator between these two parts of the organization. Did they learn something from it? Is there enough organizational knowledge that they need?
To repeat the question, okay. So the question was like, I started as a DevOps, and then I went into the FinOps, and then I worked in establishing the communication between engineering side and the management side, and was there enough management knowledge in the company to utilize, to use, to ride on this experience? I would say yes. The first piece of the puzzle that we put in place is a nice proof that it is. The company management really went along with the approach. Like, okay, I mean, the ABS, the first thing was the key. This is the key that we use to unlock the company. So when we proved that we can give you the estimate and the amount of money that you can save if you follow the estimate, if you facilitate the needs for the estimate. And when that happened, and when the company had actually the results to look at, that was the moment when the company said like, okay, this can be done. But that was the piece of the work that was following the company's strategy. Like, we want to save the money, and that's cool. The moment we get to the second part of the puzzle, when we said like, okay, you want to innovate or you want to be more competitive, that was the moment when company had to say, no, we are not really into that, which is cool, which is fine. The bad thing is if you as a company want to propagate this idea, but in reality you don't really want to follow through really. You want to save the money and you want to look good, so you would talk these things because they sound good, and a lot of people can align with the ideas, but not in reality. So my answer is yes, because it was, I think yes, because it was properly aligned with the current company strategy. And this is why it worked. it was still amazing how these two, I would say, gangs in the company didn't communicate well. You know, everyone wanted their stuff. If you talk with engineers, they would moan about not being able to use the cloud freely to create new clusters, to do stuff, you know. They would moan if someone would warn them that they need to clean up the stuff after themselves and all that things. On the other side, management also only wanted to control. You know what they did? They imposed strict policies on how much money you can spend. And you know how engineers got to this? They said, like, okay, we will build something that is below that limit. And as long as we are below, no one will bother us. And then in this threshold, they could do all kinds of stuff, and not a lot of them were good. So while analyzing stuff, we discovered that actually a lot of accounts that were below the budget, the limit, were very not optimized because they didn't care. They cared only on doing the daily stuff and be done with it because they were below the radar. The company didn't even notice these accounts because they were, you know, below the limit. Some manager that was leading these teams was good enough, I would say, fighter, to go on a meeting with company management, upper management, to fight for a good budget. And then after that, he would bring the hunt back, and then he would say, hey, I fought for this budget, we have enough budget, now you go and play. And these teams were really happy, but still not optimized. This helped company actually analyze and isolate these accounts as well. So again, back to the question. I think yes, because of this. The strategy in place was correct. It was about saving the money. The engineering was able to follow. The model was simple. It was easy to translate. We would invoke new, a lot of that was written in Python, some of that in Node.js, so both very popular languages. So it was really easy to invoke new engineers into the game, and they picked up things pretty fast. Small isolated pieces of code, so relatively simple approach. Yes? Why we didn't?
Use AWS cost management.
Accounts management. Cost management, yeah. So that is absolutely good question. The problem with this approach was that they were using this before us. And to properly investigate 400 different accounts using AWS cost management required them to spend a lot of time over and over looking through that. And you know, in that big company, things change on a daily level, not on a weekly or monthly level. That is a drastic changes up and down in the use cases, in the usage, in the patterns, in all that stuff. They wanted something that would be automating the whole stuff. So cost management is a good approach. It also fails to fit in to fill in all the gap about custom stuff. Like I said, they would have production load running on a dev account. And you can't just undo that load. You can't just take it out and move it into the prod account. So a lot of these gotchas, an example, they wanted us to introduce something they called big red button. You know what big red button is? They wanted us to create a UI with a big red button. They would click on the 15th of December. And they wanted us to shut down all kinds of resources throughout the company because they would go into the low usage mode until, I don't know, 10th of January. That was also part of the whole activity. But we started with one idea. 10 days later, we would have all kinds of exceptions from that rule because, again, large company, large organization, a lot of managers were able to fight their way and get the exception from this rule. So we had to avoid them. And when you go, I mean, a lot of these AWS solutions were really good, and you can use it for that as well. But when you go into an enterprise, having so many different tweaks and things, if you are not willing to dig in and build something custom, not really going to work for them in a way they expected. In the end, we were using the same stuff as cost management. So we would execute API calls towards the AWS pricing API. We would execute CloudWatch calls to get the metrics about EBS volume. So it's underneath, it's all the same stuff. It's just that it was not really usable for them on the company level. They tried 2 or 3 different FinOps specialized products for that. So products that are fully baked with all kinds of reports and all kinds of things you can think of. You know, the answer would always be like, tag everything properly and we will handle something for you. That tag everything properly does not go well with that kind of a company. It's tag everything properly with 2 teams, 3 teams, 5 teams. That's really cool. But when you think about 400 teams and you have to go in them, we also had a situation when we would go to a team and we say, hey, you need to tag things properly so the tool would be able to pick stuff up from the account. And they would say to us this, and I quote, like, when you come to do our job in every day, and when you have to also manage the existing infrastructure and deliver new features in this amount of time, then you come and you say to us, implement this. And they would just refuse. And they knew they were below the budget limit, they were bringing money to the company, and they would just say, no, not interested. You know, and that's the reality. It's one thing that when we talk about it, but this is like the real stuff. Out of time. So thank you for your time. I hope you enjoyed, and see you next year in Brno again, about something else. Thank you.
Test, test, test. Hello, can you hear me? Very good. So out of curiosity, not a full room, half, maybe quarter of the room, how many people here have used Ceph before? Almost everybody. Okay, cool. How many of you are still using Ceph today in production? About half of you. Okay. And how many of you spent time benchmarking Ceph in the past? 3, 4 people, 5 people. Okay. And how many of you enjoyed benchmarking Ceph? 1 person. Okay. Okay, cool. So today I'm going to be talking to you about SciBench, which is a new way to benchmark Ceph. It's an open source project written in Go. And I'm going to give you a bit of background about the project and kind of why we did it. But first, let me talk to you a bit about why benchmarking is painful. So it's painful for a number of reasons. You need to run tests many times. You need to run tests for a minimum length of time in order for it to be a good test. You need to, there's lots of variables, loads and loads of variables, especially with Ceph. When you make changes to a workload, you need to be only changing one of these variables at a time as you go through the tests, so you can kind of figure out and diagnose what changes are having what impact. And then when deducing those results, even if you've only changed one variable at a time, there's a good chance that more than one thing has changed and you just didn't realize. So that's always fun. So with Ceph specifically, benchmarking becomes even more complicated. The first reason is Ceph has many interfaces. So we're not just interacting with Ceph one way, we're interacting with it many ways. You have block, file, object, or you could talk directly to the Rados API. With Ceph, you have massively varying workloads. So the different Ceph protocols all have different workload characteristics. And so you need to take different approaches and kind of measure each approach in Ceph independently, figure out, okay, well, so for RBD, this actually works really well, but for S3, this is terrible, or whatever. So that's kind of another issue. Another issue is that distributed systems need distributed benchmarks. So because Ceph's performance scales linearly as you add OSDs to the cluster, you also need to scale your benchmarking tooling in a very similar way to make sure that you're not limited by your benchmarking architecture. So the drivers or worker nodes that you're using to benchmark, or client nodes as some people in benchmarking world call it, need to not be the bottleneck. You need to have enough client nodes to fill up the Ceph pipe. So another issue is that workloads can be invisible to you because many people that are operating Ceph are like, oh yeah, I'm operating this as a service, and they go and talk to their customers and they say, hey, what are you using Ceph for? And their customers don't tell them, they just say, we want an object store, or we want a file store, and they don't say what, because in many cases their customers don't know what they're going to be doing. So a lot of people that operate infrastructure are service providers, and so the eventual need is kind of opaque. So you kind of figure that out over time. That's a bit of a challenge. And then another issue with Ceph, which is always fun, is that the background work in Ceph can also get in the way. Ceph's doing all this stuff in the background, like opaque deletes, it's doing scrubbing, it's doing self-healing kind of checks, and those things are things you have to be aware of as well when benchmarking Ceph to make sure that when you look at changes you've made, you haven't inadvertently introduced another issue. So, so at first, I work for a company called Softiron, and we use Ceph as a core part of our product. And our last kind of product, Hyperdrive, which was an appliance for Ceph, we had this deployed in dozens of sites across a very large customer base, loads of different workloads, and we needed a way to figure out when we architect a new Hyperdrive cluster, what's that going to look like for a customer? And today, we offer a similar product, which is a full end-to-end cloud, and we have the same problem, which is a customer is going to be using Ceph in a certain way. How do we estimate what type of hardware to provide them? Are we providing NVMe? Are we providing SSD? Are we providing hard disk? And in some cases, kind of what combination. So we needed to figure this out as a critical blocker for our business. And so we started with this tool called CosBench. Anybody heard of CosBench? Also, the same guy that loves benchmarking. Oh no, a few more people. Okay. It was originally created by Intel. It's open source, written in Java. And CosBench was, for a while, the only tool you could do benchmarking of Ceph with. It was targeted at S3 and Object, but it also did have some limited support for Rados as well. And it was originally designed also to benchmark other object stores, so you could compare like your Ceph deployment to an S3 deployment, or your Ceph deployment to Google Cloud, or something like that. So we used this for a while, and we didn't really want to reinvent the wheel. But there's some problems with CosBench. The first problem is that the JNI is expensive. If you want to use the Java native interface or use CosBench to measure performance for anything other than S3, because Amazon does have a pure Java implementation of S3, but for everything else, it has to you have to traverse this native interface, and that's very expensive. So it completely defeats the point of doing benchmarking from CosBench. There was a number of other problems with CosBench, which is, first of all, it didn't really have a maintainer and didn't see any code contributions for years. So the Intel guys kind of abandoned it after a while. I guess they either moved on with their lives or stopped using it. There's also using this thing called OSGI, which was this horrid kind of bundle-based Java kind of. It was very much built as a monolithic application. And so CosBench was originally targeting lots of different object protocols, and that may have made sense for that, but it really was a very fragile structure and didn't really work for us. So there were a number of issues with CosBench, the manual workflow, no build or install system, and we kind of spent a bunch of time with CosBench trying to figure out how can we make this better. So we tried to build it with Maven. How can we package it, document it, kind of use it in a sensible way? But at some point, we kind of just abandoned the project because it was more effort than was necessary. So we ended up writing our own benchmarking tool, and that's SciBench. So what was the goals of SciBench? SciBench, we wanted a tool that is simple and lightweight, easy to read, easy to run, easy to debug, so you know what's going on. We wanted it to be linearly scalable in the same way that Ceph is linearly scalable. So we didn't want it to get in the way or to benchmark SciBench itself. We want to benchmark Ceph. We wanted to benchmark all different Ceph protocols. This is a tool designed from the ground up for Ceph. It had to be efficient and low level. So we wanted something that lets us call out to C libraries like Rados without performance implications. And we wanted it to have similar performance to FIO, because FIO is kind of an industry standard for benchmarking and is pretty low level itself. And FIO is great, frankly. And so we kind of wanted to be able to look at FIO and see some numbers, and look at SciBench and see some numbers and see something that made sense as a result of doing that. Those main goals. And then the final thing is that we wanted to have some framework that gives us control over the data that we use to run the benchmarks. So basically, we want to also control what data we're generating, not just using like dev random or something like that, right? So what's the architecture for this? It's written in Golang, so it's almost free to call out to C. It's both a daemon and a CLI tool, so you use it like a command line tool, but it's also running on your driver node as a daemon. It handles auth, so it takes the Ceph keys where necessary and the S3 keys where necessary as arguments, and it passes them to the monitors of the gateways as it needs to. It's multi-threaded, so because it's written in Go, it's fairly easy. But also, by default, every SciBench driver spins up a thread per CPU core on the worker node, and so you can control how many threads you want and play with that as a variable as well when you're doing benchmarking. And that could be useful if you have for specific workloads that do that. It does both bits or bytes. Networking people seem to love measuring things in bits. Storage people seem to love measuring things in bytes. No one cares, divide by 8, whatever. Then it also has this control of ramp time, which many benchmarking tools do. So you specify a kind of uptime and a downtime, and then it won't really measure the first 3 seconds or the last 3 seconds. And then finally, SciBench also is not focusing on it's only focusing on the benchmarking. It's not focusing on all the setup and like talking to the monitors and capturing like the data and figuring out. We figured we wanted something that just did the benchmarking, and then we ended up writing another tool, which I'll talk about in a sec, called Benchmaster, and that was a tool that kind of helps you orchestrate your benchmark, run sweeps, run multiple things. So I'll talk about that in a second, but Sidebench is just about running one workload and doing it well. So what's the architecture of Sidebench? You can see on the right here, you've got a Ceph cluster, you've got librados, librd, libcephs, rados gateway, librd, and libcephs twice to demonstrate, to demonstrate the file system. So there's, from a Sidebench worker, you can either talk to Rados directly, you can use RBD images, you can use a mounted file system, you can use Rados Gateway, or you can talk, the last two are kind of native. So this is like either a native file mount or a native block device. And so you could theoretically use Sidebench to benchmark stuff that isn't Ceph. You could benchmark anything. So that's kind of what the architecture looks like. So for librados, you just provide a Ceph pool, a Ceph key, and a monitor address. RBD, you just provide the same thing, and it handles the RBD images. The one thing, so with Rados Gateway, and this was something that CosBench did very well, is you don't have to worry about load balancing HTTP requests or figuring out how to do HA proxy or something similar in order to deal with benchmarking S3, because it kind of, every worker will can talk to a different Rados Gateway server. So there's kind of some inherent built-in load balancing just due to the fact that you have loads of workers and you can provide it loads of endpoints, and then it will do that for you. So that's pretty cool. So what's some of the other stuff it can currently do? You can do bandwidth limiting. So you can, some customers have requirements such as, hey, we want to have 100 millisecond response time when doing 30 gigabytes a second of traffic. So this is a good way of getting latency numbers at a specific bandwidth. When you max out bandwidth, that's not always a good indicative measure of latency. So it's a good way of limit workers from maxing out the pipe. So you get a really good view of kind of what latency implications is this workload going to have. It has a slice generator, so by default it generates random data, but it's not very useful when you're trying to measure things like compression or deduplication. So you can put that random data into a buffer and then use the same data again for future workloads in order to see the impact. You can do read-write mixes, so it's not just about doing a read workload, doing a write workload. You can also do like a 30-70, 50-50 split at the same time, because most workloads are going to be combined. Sidebench also has support for individual statistics, so you can write out all of the stats from a worker, and then you can go away and do statistical analysis and a whole bunch of other kind of investigation to figure out what you want, what actually really happened if the numbers don't make sense. This ends up being like really, really big file, so it's only worth doing if you're really confused. And then finally, Sidebench doesn't delete anything. It doesn't clean up after itself by default. You can tell it to, but it's because deletes in Ceph have a huge impact on performance, and they're also silent. It's hard to tell when they're happening. So, so we don't do deletes by default, but you can turn it on. And then that gives you kind of a representative view if you're doing loads of deleting. So Benchmaster is a small wrapper for Sidebench and also for CosBench as well, because we kind of had a migration process moving from one to the other. It's for running a series of benchmarks rather than just a single one. It allows us to kind of provide a set of options that we can sweep over. So I can say, hey, go and run a workload for 1K object size, go and run a workload for a 4K object size, 16K object size, and then come back and give me all the answers. And then finally, it also writes to Google Sheets. So with Sidebench, I can generate a Google Sheet, and then all my kind of workload data ends up in there, and that's just a very easy way to draw graphs or use the output collected over time, so it's much more organized. So I want to show you guys kind of what a Sidebench workload looks like. figure out, hopefully the conference, can you still hear me? Hopefully the conference internet will allow me to do this, because I'm actually just doing it on a remote machine. Is it here somewhere? There it is. Cool. Cool. So, you can see I have this Ceph cluster. It's just a small Ceph cluster that we have in one of our Berlin labs. It's backed by, it's actually backing an OpenStack cluster, so I could theoretically make lots of people's lives miserable if I do the wrong thing. That's fun. It has 36 OSDs, it's just 3 nodes. You can see, yeah, they're all hard disk across 3 nodes, and they're all up. It's looking fairly healthy. There's some data on the cluster, not too much, about 3 terabytes used. So that will all look pretty familiar. So what's Cybench? So the first thing is, I want to show you that Cybench is actually running. And for this demo, we're not really interested in like the actual numbers, like the benchmarking data, because it's a very small test cluster. So it's not really about like hitting really big numbers. This is just about showing you how it works. So here there's Cybench is running as a daemon, and that's kind of how it works. And then we also have the command line tool, which has a fairly big help menu. But basically, for any one of the Cybench commands, I can then provide it a list of servers. And those servers will be the worker nodes. And you can run this command from any of the worker nodes. Doesn't really matter. As long as it has the daemon there, it's listening. It has an API that we'll just talk to, and it will send out the benchmark. Other things to point out, yeah, you can see the different sections. It has a man page as well, which is always nice. So some information about kind of benchmarking with Cybench specifically, some guidance, more detail into like every different command and option for the tool. There's also like a website and some information on. There's also a website which will give you detail on kind of how to download it and package it and stuff. Is that better?
I hope so. I got the response that it was not big enough.
Not big enough? Okay. I hear that a lot. Right, so next we're going to do just a basic benchmark. So yeah, so I've got some historical, let's see, commands, some of which worked, some of which didn't, so I'll run the ones hopefully that do. So here I'm going to do a Rados run, right? So this is going to be uptime 1, downtime 1, so it's just going to be a 5-second workload, and we're not going to measure the first or last second. I'm providing it the Ceph key, which is I'm just including the command to print the key, and then I'm giving it the monitor at the end. So let's see what happens. So very simple. We've got a write stage, a prepare stage, and a read stage. The prepare stage was actually skipped because I didn't clean up the data, so it could just go back and read the written data. You can see that the reads were faster than the writes. Very simple. So the next thing I'm going to do is I'm going to use Benchmaster to create a sheet. And I've actually done this before. This is the Benchmaster help page. And you can see here I have sheet create, so I can give it a sheet name and an email address, and it will create a Google Sheet and share it with me. So let's try that. Benchmaster, can't spell. Sheet create DevConf.CZ, and then I'll send it to myself. So I've just got an email, open it up, and that's a very small spreadsheet. Whoops, that's a very big spreadsheet. That's about right. Cool. So there you can see the spreadsheet, and then let me go away and run a benchmark. So, whoops. All right. Try and juggle seeing things on this screen and that screen. Oh, what's the cursor? There we go. Cool. So now I'm going to pass, I'm going to run a benchmark. And the sheet I'm going to provide is the one we've just created, right? So DevConf.CZ. And you'll see here that I've got a, I've added a new option, which is the object size. And I've added 128, 512, and 1 meg. So we can see the different speeds at these different sizes. And I'm going to make this a 5-second runtime as well, so that we can actually, it doesn't take absolutely ages, because it's going to do 3, right? So I'm going to leave that to work for a bit. And as it does that, I'm going to talk to you about the rest of, just go through the next slides. We can come back and review it in a sec. If I can figure out how to manage this. Okay. So some of the ideas for the future with Sybench. So we thought about doing a workload generator. So this is something that over time we realized is quite hard to map customer workload or Ceph user workload to something that we're going to be that actually creating a benchmark that represents that. And so, and also the invisible workload problem, we had service providers that just like, we don't know what people are running on our system, sorry, so just give us something that works for everybody. And it's like, well, but that's not really how benchmark or computers work. So we wanted to have something that we could kind of sit there, like a generator, and say, okay, here's the workload that's kind of been on average over the last month. And here's a benchmark for Sybench that you can run to test other potential clusters for this workload. So that was something quite cool that we haven't got around to doing yet. We also wanted to do sweeps over OSD counts. So this is quite cool. Actually, I wrote a script that did this, but I never actually patched it into Benchmaster. And so the idea here was, if you want to see, like, prove to yourself that the Ceph that you're deploying is actually scaling linearly in performance, what you can do is remove a whole bunch of the OSDs from your Ceph cluster and then kind of add them in gradually over time per node. So let's say you have 20 nodes, you just scale it back to 3 nodes, so you could just do a basic triple rep, run a benchmark, add in the 4th node, run a benchmark, add in the 5th node, run a benchmark, and then watch. And then if it's a linear graph, then you're happy because it's scaling linearly as was promised by Sage and the other gods. But if not, then you're in trouble, right? So, so I actually did this many times, and it did work really well, but just never got it into Benchmaster, so that would have been nice. So meta operations, so there's a whole bunch of stuff in Ceph that isn't just like running like reads and writes, and there's other stuff that you might want to do, and so it'd be cool to look at like how do you measure the impact of a snapshot or other things. There was support for Kubernetes, so obviously Kubernetes has a fairly mature CSI driver for Ceph. It works really well, both file system and block, and so it would be cool to figure out, hey, can we have Benchmaster go away, spin up a Kubernetes cluster, spin up a bunch of pods, map the storage class or the kind of the persistent volumes into pods, run the benchmark, spin it down, and then spit out the results, and then kind of make that a repeatable process. So that was something we never really kind of got around to either. And then yeah, if you guys have any ideas, either leave an issue or merge requests, patches welcome. It would be cool to see what you guys have, if you have ideas as well. So while I've been talking, hopefully, if I can find my cursor again, we can see that this benchmark is completed. And remember, I ran 3 benchmarks with Benchmaster, so it would have gone and told Sybench 3 times, go and do this, go and do that, go and do this, and then spat out the results in the spreadsheet, and there we go. So we have 3 results. You can see they're written with Sybench, the different sizes, the time, we can see that the write bandwidth differed massively between the different 3 object sizes. Same with the read bandwidth. Seems to have interestingly gone down between 128 and 512, which seems kind of dumb to me, but probably because I did a 5-second run or something. And yeah, that's the benchmark. So yeah, any questions?
I'd like to ask if there is some kind of support for like 5M. Let me say, you have mentioned that you've been basically like trying to mimic how the I/O works, and if I/O has support for 5-based config, like let's say configuring the benchmark run, is there something similar?
So is your question, the question is, can you take an FIO configuration file and use it with Sybench?
Not exactly. Is there a similar approach? Can we not to specify every time the command line way, but from the line?
There isn't, but I actually do really want that as well, because doing it on the command line is very annoying. So, so yeah, we can add, that would be a very trivial change to add as well. It's just about, yeah, exactly. So, but yeah, that's a very good question, and I think we should do that. So that's another idea for the future, albeit a minor one. Cool.
Is it possible to count IOPS performance?
It does, yeah. So, yeah, the question was, is it also possible to count the IOPS? And over here you can see there is a latency value which translates to IOPS if you multiply. That's basically IOPS, but it's just latency in milliseconds. Cool. Any other questions? Bavar?
Yeah, thanks. Very interesting, very much required tool. So just on a light note, so it means you have finally given up hope with these CBT tools of Ceph, benchmarking tools?
Well, so CBT, so the question was, have you finally given up on CBT? And I never gave up on CBT. CBT is a wrapper for lots of tools. And so in a way, it's kind of like the Benchmaster thing that we did. And actually, I gave this talk in at the Ceph, one of the Ceph days a few months ago, and the guy that wrote CBT was in the room. And he was like, hey, we should talk about integrating Sybench into CBT. So I think that would also be a very cool thing to do. But I haven't played enough with CBT to be able to say, you know, the value of like comparing it with FIO, or I know it has support for Rados Bench, it has support for COS Bench. I think it has support for another one of the Go-based benchmarking tools. So yeah, I mean, I think that's a worthwhile thing to look at, but it's it wasn't useful for us for our purposes. So we wrote this very much kind of for what we needed. But that's a good question. Cool. Any more questions? Well, thank you very much.
Should we start? Yeah, I guess so. Okay, so hello, good afternoon, everyone. My name is Miguel Duarte. I'm here with my colleague Daniel Mellado. We both work for Red Hat. I work in the OpenShift virtualization networking team, and he works for OpenShift monitoring. So we're here to present a talk titled Mayday, CNI Overboard. This will make sense in a few minutes, I hope. So first thing we'll do is explain a little bit what is the current state of the CNI project and what actually led us to care about this. Then we'll introduce CNI and Multis for us to get like a total understanding of, let's say, of the lingo and be able to properly specify the problem. From there, we'll enter a new Kubernetes enhancement proposal about multi-networking and go to the upcoming CNI release. Well, this is not an upcoming CNI release because right now it's just like a set of requests for enhancements. Like there's just a list of issues. That is something that is on scope to be worked on CNI 2.0, but it's very important. And then we'll finalize with what we've learned and where we see this going forward. So the first thing we should spend a little time to discuss is the relationship between CNI and Kubernetes. So for that, first thing is Kubernetes networking model is something extremely simple because it basically just says that every workload, every pod, gets a single interface in it with an IP address, and every pod, independently of where it is scheduled, will be able to communicate with any other pod in the system through that single IP on that interface. That interface is created and configured by CNI, which stands for Container Networking Interface. Now, you look at this like that, you get the impression that these two things are actually like bound together in a way. The reality is this thing in the middle actually does not exist. And what you do have is that Kubernetes understands something called CRI, which is the runtime interface, and this thing actually speaks to CNI. What this means is that there is no way for CNI to actually communicate to Kubernetes in any sort of way, nor Kubernetes knows anything about CNI. It really does not know it even exists. On top of that, another thing that is missing from here is, so let's say that your workload, for whatever reason, it actually like requires more than one interface. Like you have one, Kubernetes gives you that, it manages it, but it just gives you one. What if you need more than one? So for that, we didn't create, but there's a project called Multis that is responsible for that. Its value proposition is that enables the pod to have multiple networking interfaces. On top of that, this Multis thing actually understands Kubernetes. It speaks its API, and it actually speaks also with the CNI API, which we'll see later on exactly what it is. But yeah, so we have Multis that is responsible for these two things. It speaks Kubernetes, and it grants a pod the ability of having multiple interfaces. These multiple interfaces might not be only a virtualized interface. Sometimes you actually need to tap into like a physical host interface, like for instance, SRIOV. You might need that. And for that, you need to add more stuff into the picture. Like you need to use a device plugin. You need to use a thing, SRIOV network operator, which requires Multis, by the way, to be able to get your pod, your workload, an SRIOV interface. Like the picture is getting like more and more complex depending on your use case. Like the more things you need, the worse the picture becomes and the complexity increases. And this is what we have today, like all these things. And there are new initiatives coming up, like for instance right now, this DRA, Dynamic Resource Assignment, this thing got merged on, I think it's alpha for Kubernetes 1.26 or 27. And now what we have is a new emerging community enhancement proposal, Kubernetes enhancement proposal for native multi-networking. And this is what we'll focus on later on this presentation. said all this, so I'll hand this over to Daniel.
Can you hear me just fine? Okay. So Miguel introduced us to a little bit about what's CNI, what's current status, what is the evolution, but I just want to go ahead and go a little bit more on that. So first of all, CNI, it's basically, everybody thinks that it's basically Kubernetes networking, so we got all the plugins, but there's so much more to that. So I don't know if you have ever wondered why, if this is Kubernetes, why a CNI plugin doesn't have, let's say, a native config. In case you don't know, it configures on JSON, so you may be wondering why JSON and not YAML, and why not a CRD, and even more, why there's no daemon. So currently, this is just a quick overview about what's going on in a Kubernetes node when we are just having all the components over there. So currently, a CNI plugin, in the end, it's just a binary, which speaks JSON, and it's a binary that is being run by the kubelet or the container runtime, CRI. That's what Miguel was saying before. What do we want out of that? In the end, we just want a network namespace with an interface or more, but we'll get to that. But in case you're familiar with any another projects of virtualization infrastructure whatsoever, for instance, let's compare that to OpenStack. In case you're familiar with OpenStack, such as I know a lot of people here are, you can just get a VM with whatever amount of subnet and interfaces you'd like to, but you can't do that natively in Kubernetes. So just recalling that, this is a binary, which is installed by a daemon set. So that means that you got a copy of the binary in every node of your Kubernetes cluster. In the same way, it has a CNI plugin path, which stands for, OK, where the hell is my config? So when you get the binary, it's going to be looking for a config file, a JSON file with the same name as the binary itself, with the and we'll be seeing some examples later on. What is the CNI spec? So far you know that CNI, OK, is it a plugin? It is a protocol. It's an API. So in the end, it's just a specification. It allows you to use 4 primitives that are CNI add, del, seg, and version, and even more. Out of those 4, most of the CNI plugins that you'll see around only implements 2 of those, which is CNI add and del. That means, OK, give me a port. OK, delete that. And there's some complexity out of that because, as I was mentioning before, this is not a daemon. So all the implementation gets down to the CNI plugin writer. So if you want to have, I don't know, a controller out of that, OK, go ahead and implement that. The CNI spec, it's totally OK, and it only expects to read some JSON config file, some env bars from the system, and it will just execute the binary and give you a result. So I think it's worth just taking a quick look about this. So you got a couple of environment bars here, CNI command. OK, what the hell am I running? I'm speaking about like these CNI add and del commands, and then I need basically which network namespace I'm going to be using, which interface name. Recall, there's going to be only one, just like the Highlanders, but you know, there's more than that. And then the container ID. And if you see, again, here, like on, you know, I can't point out, but it's over here. Like this is just some kind of JSON in which you have the CNI version. Depending on the version that you're using, you may have some limitations, but I won't get there unless somebody specifically asks for that. And you get your CNI plugin name and the type, and then you can do whatever you want to. Once it's there, it's going to be executed, and it'll give you an out. If you have been to some other sessions, you may have been hearing about the previous results, and that's because you can also do CNI plugin chaining, which means that you can put several of those in a pipeline. And basically, if everything goes well, you get an execute code. You get 0, everything goes well, OK, go on. And then goes Multus. What's the problem here? I've been speaking about that we only got one single interface per pod. That's an acute limitation, especially if you are working with some telco environments, because the most basic telco workload is going to be a firewall. And how do you do a firewall if you only got one single interface? Good luck. So Multus is a project which aims to be some kind of meta plugin, and it handles, well, first of all, it handles several interfaces over there, and it's going to be, first of all, allowing you to use a CRD. OK, hey, finally, this starts to look like some Kubernetes native. But don't get me wrong. In the end, this CRD, it uses an object in Kubernetes called network attachment definition. But hey, it's going to be just a wrapper for this old-style JSON. This is something that we would like to change in the upcoming CNI 2.0. But yeah, I'll get that for later. So for now, what I want for you, if you get anything out of this, is that, first of all, Kubernetes native only allows you a single interface per pod. Use Multus, you got several. So this is a quick example of this. So you got let's use Flannel, but I don't really care about this, which plugin we are using. You can use any plugin for the community, Flannel, OBN Kubernetes, whatever you like to. But most of the using Multus, you get another, if you see here, another net 0 interface, net 1, net n. So you have several of those. And thus we can start doing something which is pretty much more interesting. So what are the pros about the current approach in CNI? So first of all, it's super simple. Basically, even if I stated that there are 4 primitives, basically I don't give a damn about anything but 2. So I want to create a port, I want to delete a port, and well, second version are interesting, are cool, so you know which version I'm using about the plugin. But you know, if you see, I don't know, let's go set some fancy CNI plugin. If I recall correctly, so if you will go and do a git blame, you may get me wrong, but Cilium doesn't even have CNI check implemented. So that's just nothing, you know, like nothing fancy. But again, so this is no daemon. So any developer should have to reinvent the wheel and create their own reconcile loop for any CNI plugin, which kind of sucks because why would you like to, you know, reinvent the wheel for every CNI plugin? And also, for the same reason, its lifecycle is somehow limited because let's assume you got one CNI add, it doesn't give you an act, it just gets you a result. So what happens if you fail for deleting something? You may be leaking resources, and you may even not knowing that unless you implement your own solution or your CNI plugin. And also, CNI, to be honest, although I think it's a super cool project, the community is getting somehow smaller, which is really bad, so feel free to go join up and contribute if you want to. We are totally happy to, you know, get patches, pull requests, docs, comments, whatever. So really pleased to so. Take a look at cni.dev. The thing is that its docs could be really enhanced. Again, pull request accepted. And also, there's Podman is also somehow replacing that with some newer implementation. And as you were seeing in the original diagrams that Miguel was showing, it's not really Kubernetes native. You may say, why? But you are saying that it's a CNI, container native network interface, and what? But this is because originally CNI was meant to be used with Rocket, which some of you may know. It was a container interface, we're able to some of the other implementations that we have. So it's like it goes a long way backwards, and it's not really that native. Why haven't you just migrated that to YAML and proper CRDs? Well, it just evolved that way, so we plan to change that with upcoming new specs in 2.0. The good thing is that it's super simple. What happened here? OK, thank you. So what's the deal here? As I was saying, this is super simple, just 4 different primitives. It's totally simple to do a CNI plugin and scale. There's even some examples on that. If you go to my GitHub and you say the kubecon CNI, you can just see that I wrote an example CNI plugin for the kubecon in Valencia, and it does nothing, but just fork it, and it'll allow you to get a fully working CNI plugin for your own. But also has some limitations, and in the end, it's just a 2-trick, let's say, pony, which is add, del, and that's it. So far, and now I'm going to be getting back to Miguel because I want for him to highlight you a little bit of some things about theirs. Currently, it's a KEP, which is a Kubernetes enhancement proposal, which is ongoing about, OK, let's make this really Kubernetes native. And how? So we would like to use CRDs, we would like to use objects. There's a caveat to this, though, because the current proposal aims to be implementation agnostic. So that means it could evolve in a way that would totally ignore the current CNI ecosystem, let's say. We would like, at least CNI maintainers and CNI developers would like to avoid that, because we would like to see that it's backwards compatible and it works fully. So CNI gets evolved rather than substitute. And also this may lead to, if some of you guys are working on support, if this goes on, we would like trying to do some migration path. Anyway, so I'll let Miguel go ahead and explain you a little bit about the, this proposal, but we'll get back to you later with some Q&A.
All right. OK, next slide. So I'm going to explain the current state of this Kubernetes enhancement proposal for multi-networking. So the first thing about it, it's being split into 3 different proposals, actually. Like the first focuses exclusively on use cases. It's a quite thorough list of use cases that actually takes into account lots of things that we think are missing from the original specification. Like it has as use cases stuff like hardware devices. It's mentioned there. Hot plug into the pod. Basically, like this means that you'd have to react and actually introduce a new interface to a running pod. This is something that is not very Kubernetes, but there are use cases that require it. Then the second one is about defining the API. So it's like the one we are currently on. And finally, it would be a final cap that would basically introduce these code changes. As Daniel said before, this will be implementation agnostic. So every time in these discussions that you ask for something specific, like you want to, for instance, plug some runtime information from a pod. So a pod requests a particular IP, or a pod requests like a particular MAC address. So the reply usually is that is implementation agnostic. Like we might not care about that, and we are providing one single implementation. And it seems to be a little bit cloud focused. But on the good side, if you look at this, there are a lot of things you'll get for free. Like you'll get a Kubernetes native way to interact with the network plugin. You'll get an in-tree Kubernetes native way to have multiple interfaces on your workload. So this means like all the entire ecosystem that I've shown in the beginning with multis and all that, like half of that is actually not required. You have stuff like dynamic interfaces are featured in the community enhancement proposal. Hardware-based devices are also mentioned as an objective, which pretty much will simplify the original diagram by a lot. Like half of those balls will disappear, which will simplify by a lot the complexity of the solution. And finally, you get a native integration with things like network policies and services, which are, of course, also part and native to Kubernetes. And I would just like for you to take a look at, so here in the left, this is what the multi-CRD looks like. So you just, oops, you just give it a YAML with a packed JSON thing in it where you can put pretty much everything you want. So if you forget to put a comma here, this thing will not work. Like it's JSON packed within a YAML. It really looks bad, it's error prone, and it's hard to get right. While to the right, what you actually have is YAML, simple, like it's very easy to understand and obviously to get right. Now, another thing that happens nowadays with CNI is whenever you have to address one of its shortcomings, like for instance, reconcile a resource. Like if you are an IPAM plugin, you manage IP addresses, you need to reconcile those IP addresses. This is done at the on a case-by-case, that's done case-by-case. So every plugin that you have will need to be able to do that. If you want to have dynamic interfaces, you will need to find another way for that. So for instance, what we did was to create a controller that looks at the annotations of the pod, sees an annotation change. It computes like the delta between the interfaces it has now, the interfaces that you want to have, and will then like either add or remove interfaces. So we added a new controller. We had to redesign Maltas in order to be able to receive more inputs. So it's like a huge amount of work whenever you need to CNI to do something it was not built to do. Again, the one-trick pony knows one thing. This one actually knows two, but that's what it does. For instance, for Slack, there's no way for you to do this like natively. And there are people that are after these things. Now, not everything is bad. You have the upcoming CNI 2.0, like as I said in the beginning, all you have is like a list of issues, but you can opinionate on them. You can say what's your opinion. You can try to raise their priority, but there are lots of things that are being considered right now that will make this easier and better. So it is considering demonization. So instead of it being like a binary file just on a host file system that will be invoked, it will be run in a pod that is managed by a daemon set. That's a lot better. It helps you to add another lifecycle methods. It will be easier to deploy, and of course, it's Kubernetes native. You'll get an enhanced lifecycle, so there's a particular issue for this, and the most important thing here is they're planning on adding a garbage collection verb. So instead of you having to write a controller to reconcile your IP addresses, for instance, you'll add a verb in CNI that will actually do that for you. So it will simplify your life quite a lot. Again, this is just like an idea right now, and it's being planned. Another thing, plugin events. So this is actually a way for CNI to feed back information into Kubernetes. So for instance, let's say that CNI actually sees that your pod got a new IP because of Slack. So it will introduce that new IP address to kubelet. And finally, also device interactions. Okay, as conclusions, what we have right now is that this multi-networking enhancement proposal is very strong in terms of use cases. It basically addresses like all the current limitations of CNI, at least as we see it, and it kind of addresses the entire Maltas feature set. So hardware devices, it is native to Kubernetes, and it allows you to add more than one interface. Come on, it's multi-network. All of this put together makes that, well, CNI 2.0 better be good. It has like one chance to do things right, or it will actually probably become extinct, or at least that's what we are concerned about. And well, you can help. Like you could give feedback to the existing issues. Like if you think that you as a CNI developer could get something, like your life could be easier in any way, just comment, like ask for it, and it will probably be like taken into account quite for sure. And yeah, we have no doubt that this is where we are. Like Kubernetes users will go on and live a long, happy life, but CNI is freezing in the water and probably, like, it will probably die. The fun thing is that probably there's room for everyone, and they can still fit together and find a way to be happy. And yeah, thank you. Any questions? Oh, that's very important. So there's a weekly meeting about bi-weekly, so like twice per month. Of this multi-network community and Kubernetes enhancement proposal. And all the caps are online. You can look at them, comment. So welcome to do that. Yeah, if you have any questions, like now's your time. And if not, well, thank you for your time. Oh, sorry.
So, question regarding this multi-net cap, because in like last 2-3 slides, it sounded a bit like there is this implicit assumption from your side that this cap is about CNI 2.0.
No.
In reality, it's about redesigning Kubernetes
Totally true.
It sounds way heavier than saying CNI 2.0. So now, isn't this cap somehow going into direction of us cutting into Kubernetes 2.0? Because if I start thinking about potential migration path or river data migration, if you start and it goes wrong, it sounds like there is so much stuff that can explode that thinking like this can get accepted and we cut into Cube 129 now. This is a Cube change. So what is your stand?
Like,
Hold on, Miguel. Yeah, somehow.
Oh, I need to repeat the question. Well, it was very, very, very long, and I'm really sorry. I would really hope that we could kind of make this a little bit more interactive, because there's one thing that I noticed that if you ask me that question, it's because I did not explain this properly. I'm not saying that this cap has anything to do with CNI 2.0. Those are two different things. CNI 2.0 is on one track. It is trying to do something, and at the same time, this thing is trying to do kind of what these guys are also doing, but in a native way, and they're trying to specify it. So both of these entities are trying to address the shortcomings of what you have right now, right? And one of them is native, and the other one is like an improvement over what you have nowadays. So would you like to rephrase your question with this in mind? Like, I'm not saying that the cap is about CNI 2.0, because they're really not.
Yeah, so now my long question becomes two short questions. So first of all, I take from your presentation, like you are on the side of CNI 2.0 guys. Having said this, aren't you scared of the multi-net cap?
Yeah, so the question is if we are scared of the multi-net cap as someone that looks like we are pro CNI 2.0. So the thing is, I think there's room for everyone involved. Like, first off, I really think like all the advantages that you get on this cap, like those are real, and that's the real way to do things forward. Now, what we want to have is a CNI 2.0 way of keep being relevant. We still think it can still be relevant even if this thing enters, because like part of its problem is also, part of this multi-net cap power is also its weakness, or the other way around, like its implementation's agnostic. Like it can be just a wrapper over the existing CNI, or it can be something totally different and replace it, or ignore it somehow. Yeah, you can just combine them, which is be a wrapper or combine. There's plenty of ways this could go.
Okay, so now
second.
Can this multi-net cap make it still into Kubernetes 1.x, or is it so big that it means we are cutting and going to Kubernetes?
Wow. So the question is, this multi-network cap, it sounds like could it be ambitious enough and traumatic enough to the existing code base that you would actually need to bump a major release of Kubernetes? And the question is, I really don't know. It might, in the meetings we've been, that was never addressed that I remember.
No, not at all.
Not at all.
I mean, we haven't reached that part yet.
Again, like as far as the way that you configure the default network, actually now that I think a little bit about it, the answer is no, like because Kubernetes only cares about one interface, right? That thing will be configured the same way. This thing will just give you the ability of adding more things to it, so you can preserve exactly what you have today. I guess that eventually they will, they will adopt the common or the pod default network as one of these multi-networks. I guess that's the overall direction they're going, and once that happens, it might make sense to do what you're saying.
Does it make sense? Thank you.
Yep.
What about hardware devices? Is the new cap still going through Kubernetes device
plugins? So problem ticket? I really don't know.
Device plugins, or if there are still device plugins, if they still make sense, how can they communicate
Yeah.
data back to
So the question is if in this KEP, does it still makes, will the hardware devices still be, will it still use device plugin to actually grant the pod access to the physical network device? So we really don't know, but because that is only really listed on the use cases.
This is a work in progress. And
Yeah,
sorry for you having to repeat that later on. So we haven't reached that part yet. So we probably may want to speak or also adopt DRA and so forth, but we don't know yet, so free to come over.
But I do think like the device plugin still has a role to play in it. Probably the thing that Multis does nowadays of acting like a man in the middle to kind of instruct the CNI plugin of which device it allocated. Well, probably this implementation agnostic thing will have to do something quite similar, but we really do not know.
So far it's high level.
It's a use case only.
Yeah, exactly.
It's listed as a use case, so it'll probably address it when, by whom, we don't know.
Any other questions around, guys?
All right, so, well, thanks for your time. Okay, so yeah. Hello everyone, good afternoon. My name is Miguel Duarte. I'm here with my colleague Kike. We both work for Red Hat in the OpenShift virtualization networking team. And we are here to present a talk titled KubeVirt VMs All the Way Down, a custom-sized networking solution for the cluster API provider KubeVirt. There. Okay, so before all that clicks into place and you understand what we're talking about, because we really don't know how savvy you are in either KubeVirt, cluster API provider, and all that, we're going to introduce these three projects: KubeVirt, cluster API provider KubeVirt, and Oven Kubernetes. Once we have a common understanding about those three projects, we can actually explain our motivation, like why we care about this and what problem we're trying to solve, the goals for the network plugin that we want to develop. And after that, Kike is going to walk us through the implementation details of this solution and show us a demo for it. Okay, so the first thing, we're going to introduce KubeVirt. So KubeVirt, first thing, is a Kubernetes plugin. It allows you to run virtual machines and pods in the same platform. It essentially runs like libvirt and QEMU process inside of the pod, and that's pretty much what it does. The tricky thing here is if you spend a few seconds to think about this, you have like a virtual machine, which is inherently a stateful entity that is scheduled and running inside of a pod, which is essentially a stateless entity on the cluster. So those things will make some tricky things in the future. And one last thing we should always have in mind in this scenario is that the networking requirements for virtual machines are a lot tougher than the ones for a pod. Mostly because of live migration. That's kind of the feature we will live and die, or live or die based on. Like live migration will be our bread and butter for this presentation. Skip this one. So let me just introduce to you this project, the cluster API provider KubeVirt. So cluster API is something that, in their own words, what it does is provide a declarative Kubernetes-style API to cluster creation, configuration, and management. So all this means that the same thing you can do with, I don't know, Ansible or Terraform or whatever to provision a new cluster, you can use this tool and it will end you a new Kubernetes cluster. It has different types of providers, AWS, Google, Azure. There's also a particular provider, the one we care about, that is KubeVirt. So this means that the cluster that you get is implemented using KubeVirt virtual machines as Kubernetes nodes. This begs the question of why would you want to do this? One of the reasons, like cluster scale. You can have like one very dense, huge cluster with thousands of nodes and tens of thousands of pods, but I'd say that's really hard to manage, and you won't see many of those. It's a lot more common to have a lot of tinier clusters interconnected between themselves. Another use case for this is like you have a cheap cluster provisioner that you can use for stuff like CI, for instance. You want to test your feature, or you want to test how does, I don't know, your application survive a DNS upgrade or something. You just create a cluster, you run your test, you tear down the cluster at the end, and you're done. Finally, let's introduce the Oven and Oven Kubernetes projects. So Oven is essentially like an SDN control plane that orchestrates a bunch of Open vSwitches that run on your worker nodes. Its value proposition is of allowing you to use like a higher level abstraction that you'd get from Open vSwitch. So instead of you getting to manage like to manage OpenFlow, what you manage are stuff like logical switches, logical routers, ACLs, and these will afterwards be compiled into OpenFlow and installed in the nodes of your cluster. So if this is Oven, We then have Oven Kubernetes, which is a CNI plugin that provides an opinionated topology and essentially translates Kubernetes objects to Oven logical entities. So let's say that you provision a network policy on your cluster. Oven Kubernetes will translate that into a set of ACLs. And those ACLs will essentially be translated to OpenFlow that will be installed on the nodes. Same thing with, let's say, services, these kinds of things. That's its task, translate from Kubernetes object to Oven logical entity. Okay, with all these things in mind, we're good to go on the motivation. So our thing is we want to decouple the node updates from the tenant cluster VMs using live migration. What I mean by this, so remember that your cluster API provider, KubeVirt, it gives you Kubernetes clusters, and it implements its nodes as KubeVirt VMs, which is a Kubernetes plugin. So you get essentially like Kubernetes inside of Kubernetes. And we call the, let's say, the topmost cluster, it's the infra cluster. The bottom ones, the ones that are being provisioned by this tool, are the tenant clusters. So let's say that you want to upgrade your infrastructure cluster. Well, we don't want it to impact the workloads of your tenants underneath. That cannot happen at all. For that, we will rely on live migration the entire time. And essentially what we have today does not provide live migration. It simply does not give us what we want. And for that, you will see the wacky thing that Kike came up with. Why Oven? In the middle of all this, why should we go for Oven? Well, other projects like OpenStack, they're already using that technology and with really good results. Like you have like, using some improvements, you get like a migration downtime of around 100 milliseconds, which is extremely good. And we want to strive for those numbers, so that's where we're trying to go for. Okay, so we know what we want, but now we have to set explicit goals on our network plugin. So the first thing is the TCP connections that are established on the node, basically for kubelet and for the workloads of your tenants, they must survive the migration. Like once the, let's say the Kubernetes node, that is essentially a KubeVirt VM, migrates from one place to another, everything that it is running must survive moving to a different node. Another thing, the IP and gateway configuration on that worker node, it must remain the same. It cannot be updated during the migration. Why? Well, for instance, kubelet is bound to that IP address. If it changes the IP, kubelet will basically go bananas and like your workloads will be impacted. Another goal that we have is that a tenant cluster cannot access anything on another tenant cluster unless that tenant exposes it via services. Also, a tenant cluster cannot access anything in the infrastructure cluster unless it is also exposed via a service. And we need to do that for two types of services, node port and load balancers. And I'm now handing this to Kike, so.
So hello, again my name is Kike. I'm a software engineer at Qubit Networking, and we have tried to find multiple products to have some kind of live migration proof of concept. So what we are going to see right now is like the big points that we need implementation-wise. So what we need is to implement live migration in the cluster default network, not doing it in a secondary network, not doing it in the feature from OVN Kubernetes multi-homing, in the default network. We will see later on why is that, why we want it in the default network, right? We also don't want to set the IP address in the pod. We want to bypass as much as possible the networking inside the pod and pass all the information to the VMs. So kind of Kubernetes is not in the middle. So for that, we configure DHCP options from OVN in the logical switch port, which means like we kind of prepare a DHCP server so the VM can consume this IP configuration, right? Also, we copy some mechanism from Calico. Like they use something that is called IRP proxy. What it means is like some parts of the topology, you can configure some parameters that is able to answer from a foreign IP address that doesn't correspond to the subnet at this level. So for that, this is how we implement IRPs for the default gateway. So the VMs has always the same default gateway independently of the node where they are running. And also the neighbor cache is exactly the same. OK, so now we are going to see the topology of the communication for the north-south communication, right? The most north part. This is going to be exactly the same before and after line migration, but the important part here are this IP address here and here, because this is the IP addresses that we use to redirect, to do the point-to-point routing during line migration, right? As we see here in these tags. All right, in the next we see the lower part of the topology, like the slide before is like the upper part of the topology. This is the down part of the topology. And this is where the point-to-point routing is being done. And for that, we have two important OVN resources to configure egress and ingress. All right, we have something that in OVN is called policy, and we use it for egress. So we say, OK, for traffic going from this IP, we want to go over this node with this IP, right? This IP is the same IP addresses I have like pointed out in the slide before. Then we have like another thing, which is a static route, and we use it for the ingress communication. So it's kind of the opposite, like, OK, if traffic is for this IP address, you go over this port, all right? So also, another thing that we configure in the topology is the IRP proxy. And as you see, and this is very important, the IRP proxy is exactly the same for both nodes. With this, the VMs are going to have exactly the same default gateway independently of the node. And most important, the neighbor cache is going to be the same. So there is no need for updates in the neighbor cache. So the downtime after line migration is slower. So the idea is to maintain as much as possible the network configuration during line migration. OK, another important part here is, as we say, the configuration of the DHCP options. So this is a kind of OVN terminology to start a kind of DHCP server, right? So what it does is just it serves the IP configuration to VMs over DHCP. And another important part is here. The pod, the network namespace in the pod interface is not configured at all. So this is just L2 communication. So IP configuration doesn't make, let's say, noise during line migration, and it's just a L2 link between the VM and OVN. And of course, the VM is receiving the IP address over DHCP. OK, then we are going to see how this bottom part of the topology looks after line migration. As you see, it's kind of the mirror. And so everything here is exactly the same. The only thing that it changed is for the egress traffic, this IP, which means like, OK, now I'm in this node, so I want my egress traffic to go over this node that has this IP address. And the same thing for the ingress traffic, right? So what we do is the same IP, but we say, OK, now I want to redirect this to the port of the node 2. And this is the topology. Now we are going to do a real demo. I'm going to explain with a pair of slides very quick the demo we are doing. It's super simple, but maybe it's good for illustrate things up. So what we have do is we have like a pair of nodes. We have a hosted cluster, a tenant, and we have the worker VMs, right? So we have a client pod that opens just one TCP connections to a server with some super dummy software that we have put there with the name TCP proof. We just open one connection, and if it gets broken, the server goes down. So it's easy to see like the pod. See, if the pod is down, the TCP connection is broken, which is very important for us. And then what we do a live migration, and in the same hosted cluster, the pod goes from one node to the other, and the TCP connection are kept. All right. So let's go with the demo. OK, so before I start, let's explain what we have here. So the first part is the latency between request and response in the client, in the client what we have seen. And in the bottom part of it, what we see is like the two pods that implements live migration in KubeVir. Because in KubeVir, as Miguel has said, like all the VMs are backed up by a pod. And during live migration, you have one pod in one node and another pod in another node. And there is one moment where libvirt communicates state between one pod to another. And then one of the pods dies, and the live migration has ended. So we will see here the latency, and here the pods of KubeVir, right? And we see here one pod is in one node, and the other is in the other node. And we see here the state. OK, let's start. OK, now it has to start. The latency, and in one moment, we will migrate it. All right. And then you see here in the status that is the target pod in the target node is running. Now they are communicating the state between the two nodes using a libvirt mechanism, like memory pages and the like. They are communicating. And now the old pod in the old node is going to be not ready. And migration is done. So what is happening here is like this proof of concept we are doing is not perfect. It's not perfect, but what we want to accomplish is like the TCP connection is kept, which is good enough for us. It's not perfect, but it's good enough for us. And this is what it is. There is nothing more here. And what we have, the rest of it is like we do again a live migration. So we see also the same IP address. All right, and same happens, but in the opposite direction. And then a spike here appear with, I know it's not perfect, but it's good enough for us for now. We have some ideas to improve it, like in OpenStack, they use something that they call multi-requested chassis, and we will see what we do with that. And that's it. ¿Dónde están las demos tú? Ah, espera, están aquí. All right. OK, conclusions. So now we explain what we are doing it in the default network instead of using a secondary network where we have like more possibles to change things up. In the world of tenant clusters, we need to use a lot of Kubernetes mechanism to implement communication with the API server that is running in the infra cluster, in the management cluster. So for that, using the default network, we have a lot of stuff for free. We have access to services. Also, we have isolation. We have like the network policies. We have all of this. Then we have seen that using point-to-point routing in the primary interfaces, so we can make the TCP connection survive and has a consistent IP address that follows the VM during live migration, right? And now with these points, what we discover is like we know how this proof of concept works, and we can start to implement it and improve it like little by little. And that's it. Questions? All right. All right.
So during the migration, if the cluster network vault would be reaching out to the host network vault for a service, for instance, would that still work?
I mean, you are going to have, so the question is about what's going to happen, if I understand correctly, what's going to happen when you receive, when they try to access the pod during live migration, right? So it depends, like if the TCP connection is already open before live migration, as we have said, the connection is not going to broke, but you are going to receive some latencies in the packages. If you are going to establish a new connection during live migration, it's possible that you are going to, your client is going to retry until it can, it can establish the connection. So it's something like half a second now, something like that. I know it sounds like super bad, but it's just a proof of concept. So this is how it's going to behave. Okay, thank you. All right.
So you said the gateway is kept the same.
Yeah.
So that means that traffic goes through the original node.
No, because in OVM, not OVM, sorry. In OVM Kubernetes, you have different logical switches per node. So all the L2 traffic doesn't escape the node. So even the MAC address and the default gateway has the same IP address, since L2 is cut in the node, it's not going to traverse to the other node. Like you have like different switches for each node. So even if it's the same, the ARP, when you use the default gateways, what it does is just replace the MAC address with the, so this thing doesn't goes to the other node because L2 is going to be only in that node, and you have the distributed router on top of it. I don't know, it makes sense. Okay. Yeah.
But in traditional Kubernetes networking, we've always wanted a pod to have a unique IP, right? But the name of your pod was obviously different because it's unique across the namespace or whatever. So it sounded like you were breaking the traditional Kubernetes networking.
Yes, we are. We are not breaking it. We are like, I don't. Yeah, the question is like, it feels a little, if I understand it correctly, it feels a little like we are breaking what is expected for Kubernetes networking, right? Like you have two different pods, they should have like different IP addresses. Yeah, that's why we are using like point-to-point routing, because like, let's say that the pod is in a very foreign node that only understand about subnets. That's why we need these mechanisms. We are kind of, I don't know how to put it, like making it more flexible, like fighting it a little. It's not a general purpose pod. It's for a very specific thing, like it's a backend for Kubernetes. I don't know if we are going to use it for everything, for something that is not Kubernetes, but yes, we know that, but people is happy about it because we prefer to have like migration than maybe be strictly about this one. Yeah, let's see. Okay, something else? Okay, thank you.
Hey everyone, I'm Surya and I'm an engineer working in the OpenShift networking team at Red Hat. And this is Patrick, my colleague. He also works in the same team. And we are both together here today to talk about OVN Kubernetes, which is the default CNI in OpenShift from the 4.12 release. This is the brief agenda that we'll be covering today. We will first start with the basics of what is Kubernetes and OpenShift networking. Can we have a show of hands if you have used Kubernetes OpenShift before? Yeah, that makes my job easier then. So once we finish the basics of that, we'll go over to saying what is OVN and what is OVN Kubernetes. And then why did we move to OVN Kubernetes? And I realize I have not explained what the acronym OVN stands for, right? So we will also look at that in a minute. And what are the differences of OVN Kubernetes from its predecessor, the legacy CNI plugin, SDN, Software Defined Networking. We will also look at what that plugin is. And finally, we'll talk about how this works, right? How does OVN work? What are all the components under its hood? We'll try to show a live demo of how everything works together and how do you get networking on your cluster. So Kubernetes networking. So the fundamentals are, every pod must have a unique IP. So you must allocate an IP to a pod that's unique across the entire cluster. The pod must be able to talk to other pods in the cluster, to other nodes in the cluster, and even to external entities outside the cluster, right? So basically, Kubernetes networking model defines that you need to have networking set up as soon as a pod comes up. And this is like the basic. However, we all know that Kubernetes is just a bunch of APIs, right? So it does not really provide a networking solution by default. And that is where we need portable plugins to come on top that can work with Kubernetes cluster. And such plugins that provide networking to a Kubernetes cluster are known as CNIs, Container Network Interface. And this is an upstream community that defines a set of standards on how a CNI is supposed to be written. And as per those CNI specification standards, OVN Kubernetes has been written. So it is one such CNI plugin that provides networking in a Kubernetes cluster. There are plenty of others out there, like Calico, Cilium, and Tria that you might have heard of, but OVNK is just a counterpart or another yet CNI. OpenShift networking, so like I mentioned, OVN Kubernetes is the default CNI in OpenShift. So OpenShift is Kubernetes plus a bunch of operators. And even for networking, we use an operator. It's called the cluster network operator. And that is in charge of deploying all the daemon sets and the deployments that are required for the network infrastructure to come up. And CNO supports two plugins. Like I mentioned, the legacy one, which is OpenShift SDN, and the new one, the shiny one, OVN Kubernetes. And that is the default from the 4.12 release. And between the CNO and the specific CNI plugins, we have a jam, which is Multis, right? And Multis is a meta CNI, we say. What it does is it allows an inception, so it invokes other CNI plugins. So it is a CNI that invokes other CNIs. So let's say, for example, in a pod, you want to set up multiple interfaces on it. So you can invoke the OVN Kubernetes or the SDN CNI to configure the primary interface for a pod. And then you can have a secondary interface using SRIOV, right? Maybe you want to have a secured connection to a storage, which is isolated. So you can use another plugin, and Multis lets you, call multiple plugins to get networking set up for a pod. So these are some of the components in OpenShift that are involved in networking. And we thought this slide is pretty cool because it shows all the CNIs that are supported officially by OpenShift. But the first two are the plugins that Patrick and our team manages. The rest of them are third-party supported vendor CNI plugins. So coming to OVN Kubernetes, right? So what is OVN Kubernetes? Let's start with defining the acronym OVN. But before I move to OVN, I realized I should tell you what's SDN, right? Because I told you that we are moving from SDN to OVN in OpenShift, and that is our story. We are here to see why that happened. So let's take a look at SDN first. And SDN stands for Software Defined Networking. It's a legacy network provider in OpenShift. It is also written as per the CNI standards. And it uses two main networking technologies. One of them is IP tables, and the other one is OVS. OVS is Open Virtual Switch. It's just a virtualization technology which creates a multi-layer distributed switch. So you get a virtual switch on each node in your cluster. That's how you can put it simply. And using OVS, SDN provides networking on a pod, right? So it hooks up and it creates the necessary entities, the flows, everything you need to get the pod up and running in the networking arena. But we also have services in Kubernetes, right? So we have cluster IPs, node ports, load balancers in Kubernetes clusters. How are they implemented in SDN? That's where IP tables come into play. So SDN uses IP tables, a lot of nested IP tables, for setting up services, and OVS to set up the pod networking. And using these two technologies, it's able to achieve the entire, it's able to manage the entire networking lifecycle of a pod in a cluster. Another interesting point is when you have pods across the nodes, you need them to be able to communicate to each other, and pod-to-pod communication on a node, often known on a cluster, often known as overlay networking, is achieved in SDN by using VXLAN, so the Virtual Extensible Local Area Network Protocol. And this supports east-west traffic. And now that we've seen what SDN is, if you now move towards OVNK, which is the star of our show, it's an open source project which provides a robust network solution to your clusters, or in Kubernetes clusters. It has OVN, Open Virtual Networking Stack, on top of OVS, right? So that's the extra piece here, which is really what you should take away from here. So SDN is also using OVS, like I said. But what does OVNK do extra, right? It brings this new piece called OVN on top, which is the abstraction layer on top of OVS. And that lets you create simple logical network constructs, right? So it maps things like nodes to routers and switches. So that makes it easy for administrators and infrastructure developers and even users to be able to see those virtual entities that are very similar to your traditional networking stack. Like this is what you see day in, day out as network administrators. So that layer of OVN abstraction gives you this huge advantage, whether you're a developer, whether you're an operator. So that's the key and one of the main reasons why we moved, in fact. And another subtle difference is that we use Geneve as a protocol because it also offers some other subtle advantages to VXLAN, like in its header, you're able to store more information, for example. So if you were to compare these two technologies on a high level, right, like the highlights of them, is both of them use OVS, right, and they're in their base. Both of them have an Internet Protocol Address Manager controller. Well, don't get too worried. It's just an IPAM controller that allocates an IP to each pod in your cluster. So it's centralized pod IP allocation. Both of them use OVS flows at the end of the day to create their network policies or any other things that you want to implement. They use either the VXLAN protocol or the Geneve protocol to achieve communication across nodes, but that's just a subtle detail. SDN uses IP table rules, like I mentioned, for implementing services. OVNK is using OVN abstraction and constructs. And I keep using the word OVN construct over and over. We will see what that is in a moment. And NATing, right, network address translation. This is required for every Kubernetes cluster so that the pods can talk to outside the cluster, so to internet. And this is achieved again using OVN constructs in OVNK versus IP tables, thus the SNAT and SDN. Now that we've seen the what, let's look at the why, right? Why did we move to OVN Kubernetes? OVN as the new abstraction layer, I think we already mentioned this. This allows for easier development. So as developers, if you want to add new features on top, we have a whole new engine that can let you create such abstraction constructs on your network topology. And that can help you easily add on new features. Versus in SDN, you had to directly touch open flows. And this is complicated. And you had to have more understanding of another yet technology. And that made things a bit convoluted. The other thing is the flexible and expandable architecture that OVNK provides using OVN. So you're just connecting nodes across the cluster using routers and switches. We will show this in detail in a demo. Versus in SDN, you were using IP tables for services and OVS flows, but it was too restrictive. You could not do many of the things that you'd want to do, like for the telco use cases. The final thing, open source, right? So SDN was something specifically created for OpenShift, and we wanted to take our project in an open source direction. So OVNK has contributors who are not just from OpenShift or not just from Red Hat. We have a vibrant upstream community, so we wanted to intentionally move in that direction. So these are the 3 wins that I would say that we get out of OVNK. And finally, coming to the how part of our story. So how does all of this actually work under the hood, right? So with any component in a Kubernetes cluster, even the networking component has some parts running on the control plane nodes in your cluster and other parts that are running on the data plane. So if we look at the control plane parts, the pods that are in violet or purple here, the OVN Kube master, that's the OVN Kubernetes component, right? And the pink ones, they are just details, you can even ignore them, but they are the core OVN pieces. So they are the bits that provide that abstraction that I mentioned. So what OVN Kubernetes master does is mainly 2 things. One, it gives out IPs to pods, right? So it allocates IPs across all the pods in your cluster. The second thing is it's continuously watching for all the Kubernetes API objects that are created. It translates each of them into OVN logical entities, and it stores these entities in a database. So this is happening across in a centralized manner in the 3 control planes. And once these entities are created, let's say OVN and OVS are doing some magic, right? So they're taking all these entities and doing the necessary plumbing and creating the flows that are required for networking to function on a cluster. And we talked about OVN constructs, so this is where they come in, like the logical entities. So if you take a node in a Kubernetes cluster as an example, and when you create a node, a corresponding thing that OVN Kubernetes master does is it translates this node into a specific switch, a router, some policies. So it does that abstraction for you where it converts a node as, okay, I need to plumb a switch for this node. I need to now create a router for this node, right? So, and then imagine multiple nodes in the cluster. So you're going to have multiple routers, and all of these are connected by switches. So you get this whole network topology, logical abstraction at the end of the day. And this is very similar to how you see in traditional on-prem networking. And another thing, like let's say namespace, right, is a very common entity that we create. In a namespace is just a bunch of pods that are tracked over there, or services, right? So if you take pods in a namespace as an example, we might want to track all the IPs of those pods. So we create a logical entity called an address set, which is a collection of IPs, right? And that's used to provide a specific functionality for features. If you take a pod as an example, a pod is translated into a logical switch port. So it's a port on a switch. So you have a switch created for each node. All the pods on that node will be a port that are hooked to the same switch. And the switches amongst different nodes will talk through a router, right? So it's basic networking here. And the same for services and endpoints. So each of them are translated into entities called load balancers, and Patrick will talk about them in detail. So those are the things happening on the control plane. And once the control plane aspects are dealt with, on the data plane that is running on each worker node in the cluster, we also have a lot of things actually going on. So like I mentioned, the master has now allocated an IP to the pod in the cluster. Once the IP is allocated, the CNI aspect, the actual binary that is doing the CNI add event, is located on the node. So the OVN Kube node pod is continuously also watching for these IP annotations that the master does. And once master has finished its job, the node takes over. And the node is literally creating the virtual Ethernet pair that's required for the pod. It's actually setting up the plumbing inside the OVS that is required for the pod to have its networking up and so on. So the CNI executable commands, like we mentioned, which is done as per the CNI specifications, is all executed by the node component. And in the node also, we have these pink magic containers that are translating these entities which we created in the database in your control plane into flows, traffic flows, let's say, right, for simplicity. And now that I've covered all the fundamentals and the theory aspect of it, we go to the cool part, which is the demo aspect, where Patrick is going to show everything that I said, but on an actual live cluster. So over to you, Patrick.
Hi, everyone. My name is Patrick. I'm from Red Hat, and I work with Surya on Oven Kubernetes and general OpenShift networking. So what we have prepared here is how all of what Surya just shared with us ties into an actual cluster. So for our general upstream development, we are using Kind. So in the recorded demo, I'll first clone our upstream repository, which all of you can easily do, and then we'll move to actually starting up a cluster. So as I said, we are using Kind. Kind is Kubernetes in Docker. So for every container that Docker creates, you will see a Kubernetes node. So we've prepared in our upstream repo a very neat script that allows you to, with one command, to create a Kind cluster that actually uses our CNI, Oven Kubernetes, as its networking. As you can see, there is a ton of options that you can choose from to set up different scenarios like IPv4, IPv6, dual stack, and all of different features that are available in Oven Kubernetes. As I said, to set up the cluster, you just need to run one command. It will take around 5 minutes to set it up. I'll fast forward here so we don't waste too much time. As you can see, we build all of our containers. We've set up the Kubernetes cluster, and at the end, we apply simple YAML files that take care of deploying Oven Kubernetes into a cluster that initially doesn't have any CNI on it. OK, just tying it back to Kind, if any one of you is not aware. As you can see, we have 3 nodes, Oven Control Plane, Oven Worker, and Oven Worker 2. These are, of course, represented as Docker containers. And we have a little bit of an exception here. And if you exec into any of those Docker containers, you can see that there is CRI-O, and you can see that there are additional containers running on our worker node. Now, moving on to Oven Kubernetes. As Surya said, we have a control plane and the data plane. The 2 top pods contain our control plane components. The first one contains Oven databases that we use to store the logical entities. That's the guy here. And the second one, Oven Kubemaster, that's the main piece that does the translation between Kubernetes and Oven. So this is the component that will create logical entities in our NBDB that will be, that I'll talk about more in the next slide. Of course, we also need to provision the data plane components, and as you can see, the next piece is Oven Kube node. This is a daemon set that runs on every node in the cluster, and you can see that in the nodes section. And it contains Oven Kube node pod. That pod runs the actual CNI. So when a pod gets created, kubelet will call the container runtime, which will then make a call to the CNI, and will take that call and provision pod networking for every pod that's cluster networked. Additionally, and that's something that's upstream specific, you can see that there are OVS node pods. These are running OVS upstream. So these are responsible for setting up the actual flows and applying them to actual packets. So after all of these layers of abstractions coming from Kubernetes to Oven, we configure flows that get applied to each packet that flows through our cluster. This is not something that we have downstream, and in downstream we have a host network service. We have a systemd service that runs on the host. So this is not possible with a simple Kind cluster since we have just Docker containers. Additionally, please note that we do not have HA here. I tried to keep it simple for the demo purposes, but of course you can enable it so all of the control plane components would be multiplied to provide the HA functionalities. the keen eye of you can see that all of these pods have IPs that are actually from the host network. This is because we are the CNI. There is no CNI to provide us with any cluster network level networking. So that's something that you will often see in Oven Kubernetes, that our data plane pods and control plane pods are host networked. And yeah, you can see that they share the same IPs out as the nodes. Let's get back to the slides for a second and talk about how we represent a cluster in Oven. Okay. Yeah, as Surya said, the cluster is represented with a bunch of switches and routers, and that's it. It's very simple to grasp if you know what a switch and a router is. So as you can see, the dotted boxes represent every node in a cluster. So here we only have 2, but you would get everything that's in the dotted box, you would see on every node of your cluster. Up top, you can see the underlay network. This is the network that allows us to connect the nodes and to provide external connectivity to the cluster. And this is not something that we configure, and it comes as underlay network, so it's provided to us, and we can use it to join the nodes. You can see here that every node in the cluster gets a host subnet. This is a subset of the whole cluster network. It's specific per node, and all of the pods in that specific node will only have IPs from that host subnet. Starting at the bottom, as Surya mentioned, every pod will get its own logical switch port. Every pod will have it created by us, so during the pod creation, we'll create a VIF pair, and one of the ends will get connected to the pod net namespace, and the other would get plugged into an OVS switch that would then be represented as a logical switch in OVN. So this gives us the advantage that if there are 2 pods on the same node, they will use that logical switch, and it's local, so there is no need for the traffic to traverse node boundaries. Now, if the pods are located on different nodes and they need to communicate with each other, they need to have something that connects them. So we use centralized Oven cluster router for that. This is a singular router that will be only one per cluster. So this gives us an opportunity to connect logical switches from different nodes, and additionally, it gives us a path to north-south connectivity. So if a pod wants to talk to the internet, it will go through the gateway router. So the gateway router is a node-specific router, and it is responsible for providing the ingress and egress functionality out of and to the cluster. As you can see at the top here, it actually takes over the default interface that's on every node. So when you provision Oven Kubernetes, that interface that was the default interface connecting the nodes will get taken over by us, and we'll manage it, and that thanks to this, we can provide external connectivity and direct traffic as we need to. And one note I wanted to make here, if your pod is host network, which means that it doesn't need the cluster network IP, it's not going to be represented in Oven. It's not going to be represented in Oven, and most of the traffic flows it does to external entities will not use Oven. So thanks to it, our CNI uses that approach, and we can set up everything before we start handling pods. Let's see how all of that looks in an actual cluster. So I've prepared a trivial YAML file that contains of a client pod and a service backed by a deployment with 3 replicas. So I did that to showcase the very minimal approach that you could take to see all of the components that Oven configures to provide the service and pod-to-pod connectivity. So how do you actually see what's there? So we applied the pods, we see them here, and they all are running. And right now, to look at the logical representation in Oven, what I do is I enter one of our pods so we can directly interact with the database. So for the remaining part of the demo, you can treat it as the left side contains what's in Kubernetes, and the right side represents what's in Oven. So what networking components have we configured that allow the connectivity between pods and services. As I said in my previous slide, we have 3 nodes, and all of them get a node-specific gateway router that we use to provide external connectivity, basically. And additionally, as you can see, there is just one central Oven cluster router that gives us the possibility to connect pods and services that run on different nodes. There are also logical switches. So every node gets its own logical switch, and additionally, we use external switches to take over the interface from the host. And we use one joint switch that allows us to basically connect gateway routers into the cluster router. OK, moving forward. On the left here, you can see pods with O-wide, which means that you can additionally look at the IP addresses that we've allocated and the nodes that the pod is running on. So here, I show the Oven worker switch. And on that switch, the first port that you see is one of our backing pods for the example service I created. Additionally, you can also see that on the same switch, we have more ports that are not related to that deployment. So all of the cluster networked pods that are on a particular node would show up here. We, of course, have a port that allows us to connect to the router, and a port, the worker port, that allows us to provide cluster network to host network connectivity. Yeah, the same goes for the other switch that hosts the default client, and additionally one of the backing pods for our service. So you can compare that to what we see in the Kubernetes world, and it matches. And additionally, we see that we have the IP addresses and MAC addresses that we've allocated in OvenK. Let's take one of the logical switch ports as an example. And this is the object that we store in the database that represents one of the logical switch ports. And one interesting thing I would like to point out here, we are using Oven port security, which is a feature that allows us to restrict the traffic that's allowed in the switch. So anything other from this IP coming from this particular pod won't be allowed. The same goes for the MAC address. So if some rogue user enters the pod net namespace and changes the IP address on the VIF pair from that namespace, we won't allow that traffic. It will get dropped, so that's a neat feature. Additionally, we also see this. This is useful if there are any issues with that port, but here you can see that it's up, so it's functioning correctly. OK, so we've talked about pod-to-pod connectivity and how those ports are connected to a switch. But what happens if a pod wants to connect to the internet, right? What we do in the gateway router, recreate an SNAT rule. So we're going to translate the source IP of that particular pod into the IP of the node. So to the outside world, the IP that's egressing the node will be the one of the node. So that's the IP address we take from the default networking interface. And then we'll unsnat, so we'll translate it back when there is a reply from the external entity. So as I said at the beginning of this part, we've also created a simple service. And you can see the details of it here. So it's a service with that IP address listening on port 80. And these are the backing pods that are the endpoints for that service. And let's see how that behaves in Oven. So in Oven, we have a construct called load balancer. And it does basically load balance the traffic from this IP address on that port into all of our endpoints that we've defined in the service. The name of this entity is matching the service that we've created. So as you can see, you can easily get the networking representation of what's actually in a Kubernetes cluster. You don't need to look at particular OVS flows. You don't need to dig through layers of IP tables, and it gives you an inside view of how the networking is configured in OVN. Of course, all of this, it's logical representation of the network. It's not something that will actually handle your packets. So what you can see here is a dump of flows that we configure in OVS. So every logical switch, every router, and every NAT will eventually get translated into an open flow rule that will be applied by OVS and its module in the kernel per packet. So it's extremely valuable when you are deploying features and when you are doing it fast to have an abstraction layer that allows you to not deal with all of that, because it is really difficult to dig through all of the layers and steps that the packet takes when it traverses your cluster. And that concludes the demo. Yeah, I'll just briefly go over the... Okay. We do have some additional features in OvenK, but we unfortunately don't have time to get over them, sorry. But you can check them out on the slides, or you can check out our OpenShift or OvenK documentation for that. And that would be it. Thank you all. And do you have any questions? So the question is OVN better at throughput compared to OpenShift SDN? That's an extremely difficult question, because to get the answer for it, you would have to specify the exact traffic flow that you use to pull that throughput. Because it's different when there are multiple hops between pods, when there are different traffic paths, and especially if you consider packet sizes, protocols, and all that, it gets difficult. At the lowest level, when everything's configured, it's OVS. So it will traverse the OVS data path, and then based on the connectivity between the nodes, this will be the engine that handles the packet. So this OVN as itself is an abstraction that in the end will still configure OVS flows. So I would consider them to be similar, but to get any detailed results, it's not really easy to answer that.
If I recall correctly, it was VXLAN limitation or something that you used at the end, and you said you had to...
We use Geneve. So with all of that, with either VXLAN or Geneve, there is an overhead, right? And it's something that you can alleviate by using something like hardware offload, right? And as far as I know, it's more difficult to get hardware offload for Geneve. But yeah, there is an overhead, and I wouldn't think that Geneve is much better than VXLAN in terms of the overhead, especially that we pump more data through Geneve because we use the optional header options in Geneve that will increase the packet size.
But we do have perf and scale runs that we do between the two plugins to make sure we don't regress as we moved the plugins. So just
that's good, but like if I have a 40 gigabyte network in ABS, right? The node says that for D105 it was like extra 1 gigabyte, right? Like there is a bit of space.
Yeah. You just need to use jumbo frames and one traffic path, and you'll be good. It seems we are out of time, so thank you all.